In the depths of space, far beyond the reach of ordinary starlight, something strange is happening. From the very centers of distant galaxies, brief and blinding flashes of light erupt without warning, vanishing in less than a heartbeat. They're called ultrafast optical transients, and they are among the most mysterious signals ever detected in the cosmos. These bursts don't fit any known pattern. They're too fast to be supernovae, too bright to be ignored, and too strange to be easily explained. Some scientists believe they could be tied to the most extreme forces in the universe: black holes spinning at unimaginable speeds, matter collapsing under its own gravity, or unknown physics playing out in real time. Others wonder if they're signs of something even more exotic. In this journey through one of the universe's strangest puzzles, we'll explore what we know, what we don't, and what these lightning-fast cosmic flashes might be trying to tell us. But before we continue, subscribe to the channel so you don't miss out on any of these videos. The story of ultrafast optical transients is a very recent one, almost embryonic in the timeline of astronomical discovery. Their detection required instruments not only advanced in sensitivity, but fast, capable of resolving events that play out over mere milliseconds. This is no easy feat. Traditional optical surveys capture changes in light over hours, days, or weeks. But these fleeting outbursts are like microflares on a cosmic scale, often hidden in data that looks like statistical noise unless filtered with extreme precision. And yet, when seen clearly, they are unmistakable. Powerful. Real. The first serious detections of such phenomena started coming from instruments like the Zwicky Transit Facility, ZTF, Pan-STARRS, and even certain high-speed photometry programs that weren't even designed to look for them. Initially, these flashes were assumed to be some kind of atmospheric noise or interference. But patterns emerged. Not just one anomaly, but many. And critically, many of them were coming from galactic nuclei, from the very centers of galaxies, often associated with active galactic nuclei, AGN, or, in some cases, apparently, quiet galaxies where no such activity was expected. To appreciate just how strange that is, we need to dive into what's normally expected from a galactic center. At the heart of most galaxies lies a supermassive black hole, often millions or even billions of times the mass of our Sun. In some galaxies, these black holes are active, feeding on gas and dust and emitting vast amounts of radiation across the electromagnetic spectrum. These are known as active galactic nuclei, or AGN. In others, they lie dormant. And yet UFOs have been seen in both types. The timescales of these optical transients are where things get truly weird. Imagine a bright flash in visible light, a few milliseconds long. That's not just brief, that's ultra-brief. For comparison, a lightning strike on Earth might last 300 milliseconds. These transients are often over in 1/10 that time or less. So whatever is causing them, it's something extremely compact, extremely energetic, and capable of releasing that energy in a razor-thin window of time. Initially, researchers considered the possibility of flaring stars, such as M-dwarfs known for sudden outbursts. But the location of these events, centered on galactic cores, not scattered across the sky, quickly ruled out that explanation. Others proposed more exotic scenarios, such as relativistic shocks and jets emitted from accretion disks, or tidal disruption events, TDs, where a star is shredded by a black hole. But again, the timescales didn't fit. TDs, for example, typically last days or even weeks. These flashes were over in under a blink. So what could cause such an event? One theory suggests that ultrafast optical transients could be tied to magnetic reconnection events in accretion disks, places where the swirling plasma around a black hole tangles up magnetic fields to the point of explosive release. Similar processes occur in our Sun during solar flares, but these would be on a vastly larger and faster scale, perhaps triggered by instabilities near the event horizon. The energy density in such a region is extreme, and the gravitational time dilation could compress events in ways we barely understand. Another possibility ventures even further from the mainstream: compact objects like Axion stars, hypothetical clumps of dark matter bound by gravity, or other exotic matter configurations could interact with normal matter near black holes, producing sudden, bright flashes as they decay, collide, or evaporate. These scenarios are speculative but tantalizing, especially given how little we understand about dark matter's behavior on galactic scales. Still, others suggest these flashes could be signals, not necessarily from alien civilizations, but from natural processes behaving in ways that mimic intentional signals. Fast radio bursts, FRBs, for example, once seemed almost artificial until astrophysicists began discovering more natural explanations involving neutron stars. Could ultrafast optical transients be the optical counterpart to FRBs? A kind of visible light equivalent of a rapid magnetic collapse in an exotic stellar remnant? And if so, why are they focused in galactic centers? That question haunts this entire phenomenon. There's something deeply unsettling about the idea that these ultra-fast flashes are not randomly scattered throughout galaxies, but are emerging specifically from the hearts of them. It's as if something deep in the galactic engine is occasionally firing off optical flares for reasons we don't yet understand. Some have postulated that the black holes themselves may be involved, not just passively, but actively generating the bursts. Others suggest interactions between stellar remnants and dense magnetic fields at the galactic core could be to blame. A more radical idea is that these flashes are associated with Planck-scale events, tiny, ultra-energetic phenomena related to quantum gravity or space-time fluctuations. In these models, the very fabric of space near black holes could become unstable under certain conditions, releasing energy in short bursts that momentarily peak into the visible spectrum. These would be akin to cosmic-scale quantum fireworks, flickering from the edge of the known physics. Detecting and cataloging these events remains one of the biggest challenges. Traditional survey telescopes, even powerful ones like the Vera Rubin Observatory, were not designed for millisecond-scale detection. But this is changing. A new generation of high-speed, wide-field optical instruments is beginning to scan the sky with an eye for the ephemeral. Instruments like Hypercam, Chimera, and Ultracam are pushing boundaries, capturing high-speed optical data that could hold the key to hundreds, if not thousands, of these flashes across the sky. Interestingly, artificial intelligence has become crucial in the discovery process. Because these events are so brief and so often buried in noise, machine learning algorithms are now being trained to detect subtle, ultra-fast spikes that traditional software might miss. These systems analyze terabytes of streaming optical data in real time, scanning for millisecond anomalies that meet the spectral and spatial profiles of a transient event. As AI grows more capable, our ability to detect these blinks of the cosmos improves, and with it, the possibility that we might one day understand them. What remains to be determined, however, is whether these events are singular and disconnected, or part of a larger pattern. Could they be periodic? Are they correlated with galactic motion, mergers, or black hole spin? Some researchers have found tentative signs of repetition from certain sources, an ultra-fast burst detected from a galaxy core, then another from the same coordinates months later. Is this a cycle? A rotating object emitting a beam like a lighthouse? Or is it mere coincidence? And here's where the mystery deepens further. Some events appear too bright for their duration. That is, the amount of energy packed into the few milliseconds of visible light seems inconsistent with any known natural process, suggesting either a mechanism we haven't yet imagined, or an extreme lensing effect amplifying the event. Gravitational lensing by the galactic core's mass could in theory focus light into a smaller region, making a dim event appear bright. But the specific geometry and timing needed for such amplification are unlikely to repeat consistently across galaxies. So why does the brightness persist? Even more mind-bending is the possibility that these events could be glimpses into higher dimensional processes. In some speculative models of cosmology and string theory, energy can bleed across dimensions under extreme gravitational or quantum conditions. Could these flashes be leaks from other dimensions, microtunnels of energy flaring into our visible universe for just a heartbeat? It sounds fantastical. But the alternative is almost more unsettling, that we're witnessing a class of astrophysical events we simply have no framework for. That these are neither stars dying, nor black holes feeding, nor alien signals, but something altogether different. Something we have no name for yet. The mystery of ultrafast optical transients grows not only in magnitude but in implication. Every new detection is not just a data point, it is a challenge. A quiet cosmic dare to decode the laws that may underlie our entire understanding of the universe. What makes these transients even more fascinating is that they don't seem to be uniform. Their spectral fingerprints vary. Some exhibit sharp, narrow-band bursts of light, while others stretch across a wider band of optical frequencies. Some are highly polarized, suggesting ordered magnetic fields, while others are not, hinting at chaotic origins. This variability hints at either multiple underlying causes, or a single, complex phenomenon that expresses itself in different ways depending on local conditions. And that distinction matters. If these events are coming from multiple causes, then we may be seeing the birth of an entirely new category in astrophysics. Something akin to the early 20th century realization that novae weren't just one thing. They were a catch-all term for many kinds of explosive stellar events that we later separated into supernovae, dwarf novae, and other distinct processes. Could ultrafast optical transients be the same? Are we conflating bursts from black hole accretion zones, exotic stellar collisions, magnetospheric collapses, and other hidden events into one umbrella term simply because they all flash briefly? If we are, that only underscores how early we are in understanding this phenomenon. But if, on the other hand, these transients are caused by a unified mechanism, if we are witnessing the signature of one single process with multiple faces, then we are on the edge of discovering something truly profound. Something that connects energy, matter, time, and possibly even the nature of consciousness itself. It may seem like a leap to go from brief optical flashes to consciousness. But consider this: the human brain is also an electrical machine of transients, operating with bursts of information moving between neurons on millisecond scales. It is not unreasonable to consider that systems with such fleeting but intense activity might have emergent properties we've never even thought to look for in the cosmos. Could consciousness, or something like it, emerge from exotic arrangements of matter and energy in places we've always assumed to be lifeless? Speculative? Absolutely. But science often advances by chasing the edge of the absurd. When gamma-ray bursts were first discovered, they were so powerful and so brief that some scientists considered them to be nuclear tests occurring on the far side of the moon. Today we know they're among the brightest events in the universe: stellar collapse, neutron-star mergers, black hole birth cries. What if ultrafast optical transients are the next great leap in such understanding? There's another angle to consider: the temporal compression of information. Think about how we encode a massive amount of data in a flash drive the size of a fingernail. Nature, too, could be encoding enormous amounts of energetic information into microsecond bursts of light. These transients could be not just events, but messages of a sort, not necessarily constructed by intelligence, but carrying complexity all the same. Just as the cosmic microwave background is a fossil of the early universe, perhaps ultrafast optical transients are signatures of some exotic energy evolution, or even symmetry breaking in the structure of spacetime itself. One truly exotic theory is that these bursts represent moments where our observable reality is brushing against another dimension or universe. In the multiverse hypothesis, especially under the many worlds interpretation of quantum mechanics, it's been suggested that high-energy interactions at the edge of black holes could momentarily entangle with or imprint upon adjacent realities. While this sounds like science fiction, the math behind brane cosmology, quantum gravity, and holographic principles all hint at the possibility that what we see as a singular universe may in fact be a projection or cross-section of something vastly more complex. Now imagine that for one fleeting moment, energy in a galactic nucleus spikes in just the right configuration to breach that veil, not violently, but subtly, optically. A burst of light that isn't from our universe in the traditional sense, but rather, refracted through the geometry of an adjacent reality. A ghost flash. A dimensional echo. Still, before one floats too far into the speculative, let's ground our understanding in what we do know: these transients are real. They've been detected multiple times. They appear in data from various observatories, under various atmospheric conditions, at different times, in different galactic nuclei. They are not instrumental errors. They are not atmospheric distortions. They are real astrophysical events. And we are seeing them more and more as our observational technology improves. The next phase in this research involves coordinated multi-instrument observation. If a flash is detected optically, astronomers now rush to point radio telescopes, X-ray detectors, gamma-ray sensors, and gravitational wave observatories in the same direction. The idea is to catch not just the light, but the full electromagnetic fingerprint of the event, and maybe even the gravitational shadow it casts. This brings us to the idea of multi-messenger astronomy, where instead of relying on just one kind of cosmic signal, light, we listen to the universe through multiple senses. This includes neutrinos, gravitational waves, cosmic rays, and more. If ultrafast optical transients correlate with gravitational wave detections, it could mean that they're tied to massive energy movements, such as collapsing stars or merging black holes. If, instead, they correlate with high-energy neutrinos, it could mean particle interactions in dense, exotic environments are to blame. One exciting possibility is that some of these events may be tied to so-called primordial black holes. These are theoretical black holes formed not from stars, but from density fluctuations in the early universe, possibly even within the first second after the Big Bang. If such black holes exist, they could be tiny, unstable, and subject to evaporation via Hawking radiation. The final moments of a tiny primordial black hole's life could release an enormous amount of energy in a flash, a perfect explanation for some UFO events. These would not only solve the mystery of the transients, but also provide indirect evidence for Hawking radiation, a long-predicted but still unproven consequence of quantum mechanics and general relativity. Confirming Hawking radiation would be like finding a golden bridge between Einstein's and Heisenberg's worlds. Another speculative avenue is the interaction of dark matter with visible matter in high-density regions. Galactic centers are known to be dense with both baryonic, normal, and non-baryonic dark matter. If dark matter can occasionally decay, annihilate, or convert into visible particles under certain extreme conditions, the result might be a short, sharp optical flare. These events could also be responsible for some of the unexplained gamma-ray emissions seen in galactic cores, such as the mysterious galactic center excess, observed by the Fermi Gamma-Ray Space Telescope. And yet, despite all these possibilities, a full explanation remains elusive. That is the beauty of frontier science. Every answer spawns more questions. Every detection deepens the mystery. Right now, research teams around the world are actively hunting these elusive flashes. Programs like the DCAM Minute Cadence Survey, the Black GM telescopes, and high-speed optical detectors on space telescopes are being refined to capture more of these events. It's likely that in the coming decade, we'll have a database of thousands of ultrafast optical transients, each one a potential clue. And still, the greatest question of all may remain unanswered: what are we really seeing? What we are seeing might be more than a simple burst of energy. It may be a signal, an astronomical semaphore hidden in plain sight. Not necessarily a message in the traditional, intentional sense, but a beacon of information nonetheless. When nature speaks, it does so in code, and in every burst of light, there's data, on temperature, on energy state, on location, velocity, polarization, and more. The ultrafast optical transients are speaking a language of intensity and timing. Each flash could be telling us something about the structure of spacetime itself. Even the most conservative researchers acknowledge that we may be dealing with phenomena that demand a rewriting, or at least an expansion, of current astrophysical theory. Consider this. There are known classes of short-duration astrophysical transients like fast radio bursts, FRBs, and now we are finding their optical cousins. And just as with FRBs, the first few detections were dismissed, debated, and doubted. But now, they are part of established astrophysical lexicons, with catalogued sources and potential mechanisms. We are likely at the very beginning of the same process with ultrafast optical transients. Their proximity to galactic centers suggests that we are seeing a form of extreme astrophysical behavior that emerges only in the presence of supermassive black holes or dense stellar populations. Galactic cores are environments of staggering violence. There are dense star clusters, rapid stellar motions, immense gravitational shears, and magnetic field chaos. Some models propose that neutron stars, or even exotic objects like quark stars, may occasionally plunge toward the central black hole. In such cases, the gravitational compression and tidal heating could trigger a catastrophic collapse or phase transition, releasing energy in a form unlike any stellar event we've catalogued before. This leads into the domain of hypothetical stellar exotica. Consider boson stars, which are theoretical stars composed not of fermions, like protons and neutrons, but of bosons, particles that obey different quantum statistics. If such stars exist, and if they interact with supermassive black holes or dense matter fields at the galactic center, their decay or merger could be rapid and energetic. Since we don't fully understand how bosonic matter would radiate energy in extreme gravitational wells, it's not impossible that the outcome is a hypercompressed optical burst of astonishing brevity. The brevity is, in fact, the signature. It's what makes these events so elusive and so alluring. Our universe is full of flickering lights. Stars pulse, flare, and erupt. Galaxies shine and dim. But the ultrafast optical transient is different. It's a sudden, needle-thin pulse in the dark, lasting less than a breath and occurring from regions that are otherwise almost opaque. That is not random. That is not statistical noise. That is a statement by the universe, just one we haven't yet deciphered. One must also wonder, if these transients exist at optical frequencies, what else might exist at other frequencies on the same timescales? Could there be femtosecond gamma-ray transients? Could there be ultra-fast neutrino bursts from similar sources? If nature uses brevity as a form of expression, we may need to build entirely new classes of detectors to listen properly. In the meantime, the best we can do is triangulate. When one of these optical bursts is observed, astronomers scramble to check whether there are any correlated phenomena in other wavelengths or other locations. Did an FRB go off nearby? Was there a gravitational wave at the same time? Was there a neutrino detected by Ice Cube in Antarctica? So far, no unambiguous matches have been confirmed. But that doesn't mean they aren't connected. It may simply mean our instruments aren't yet fast, sensitive, or coordinated enough to catch the coincidences. Another developing theory draws from quantum field theory and the curvature of spacetime around black holes. Under certain conditions, vacuum energy fluctuations could become real, manifesting as brief pulses of high-energy light due to the so-called dynamical Casimir effect. In Earth-based experiments, moving mirrors or boundaries in a quantum field can extract photons from the vacuum. Scale this up to galactic size and add a black hole's event horizon, and you might just get a sudden, localized optical flash, something born from the quantum vacuum itself. Now imagine that multiplied across hundreds of galaxies. Bursts of creation and annihilation flaring in tight intervals, like quantum scars on the fabric of the cosmos. But the real wildcard remains technology, both ours and perhaps someone else's. If intelligent life exists elsewhere in the universe, especially in ancient galaxies far older than our own, might they have found a way to harness galactic nuclei? The idea sounds preposterous, until you consider the Kardashev scale, which measures civilizations based on energy usage. A Type 2 civilization harnesses the energy of a star. A Type 3 harnesses the energy of a galaxy. If such a civilization exists, the most energetic region of their galaxy, the core, would be the logical location to base power, computation, or communication infrastructure. And if they did, how might that infrastructure manifest to us? A pattern of bursts, perhaps? Millisecond-scale optical pulses, embedded with information in polarization, frequency, or timing? We know that using lasers for communication, optical SETI, is not a new idea. It's being tested even now by our own species. Could someone out there be flashing us not with radio, but with light, bursts so brief that we only now have the instruments to see them? But even if we remove intelligent design from the picture, the implications remain staggering. These events suggest that the galactic centers are not just gravitational endpoints. They are dynamic, energetic, communicative in their own language. They are not just the tombs of stars, but perhaps the birthplaces of new physics. In each blink, we may be seeing a tiny glimpse of processes that have gone unnoticed since the dawn of time. Consider this: the vast majority of the universe's activity is silent to our senses. It is only through technology, telescopes, spectrometers, detectors, that we even know the universe is active. To the naked eye, space looks still. But through the lens of ultrafast photometry, it comes alive. It vibrates with hidden pulses. It flashes in the dark. It tells a story that's been waiting eons for someone to hear. The transients might also be connected to the broader question of entropy. Could these millisecond bursts be tiny cracks in the entropic flow of galaxies, points where high-order complexity momentarily erupts before vanishing into randomness again? Could these flashes represent fleeting reversals of entropy, where systems tip into temporary order before collapsing back into chaos? That would be cosmologically significant. We've long assumed the universe trends toward disorder. But if these flashes suggest localized entropy reversal, no matter how brief, it would challenge our thermodynamic assumptions at cosmic scales. It might even explain certain anomalies in cosmic background radiation, galactic rotation curves, or dark flow. The truth is, every explanation we've entertained still leaves gaps. And it may be those gaps that eventually lead us to the answer. Each unanswered question points the way forward, toward better detectors, more refined theories, and deeper collaborations across physics, astronomy, quantum mechanics, and cosmology. The ultrafast optical transient is not just a blip in our data. It is a crack in our current understanding. A cosmic blinking cursor at the end of a sentence we've only just begun to write. And perhaps the most compelling aspect of these transients is that they challenge our fundamental assumption that the cosmos operates on large, slow scales. We are used to thinking of stars forming over millions of years, black holes growing over billions, galaxies rotating leisurely through the eons. Yet here we are, watching entire events, potentially massive releases of energy, compressed into just a few milliseconds or even microseconds. It's as if nature is whispering that not all of its secrets are slow. Some scream by so fast we almost miss them. This idea of time compression has vast implications. If such fast events are occurring frequently but escaping detection due to the limitations of our instruments, the energetic budget of the universe may be more complex than we think. We may be underestimating how often high-energy transformations occur because we are not tuned into the timescales on which they happen. What appears quiet on one scale could be thunderous on another. There is also the question of spatial scale. These bursts might originate from extremely compact regions, possibly just a few kilometers across, but be visible from billions of light-years away. That ratio of size to brightness is enormous, and it suggests that whatever is happening in those brief flashes is incredibly efficient at turning mass or energy into light. Whether through matter-antimatter annihilation, vacuum energy release, or unknown quantum phenomena, the mechanism must be one of the most energetically dense processes in nature. And yet, we're still at the stage of detection and classification. In most cases, we cannot even pinpoint the exact galaxy of origin, let alone the precise location within that galaxy. Galactic centers are crowded, chaotic, and bright. Parsing out the source of a single, millisecond-scale burst within that noise is like finding a single firefly flashing once in the middle of a fireworks show. But with improving resolution, increased sky coverage, and faster data processing, the next few years will likely bring a dramatic increase in the number of ultrafast optical transient detections. One proposed observational strategy involves pairing wide-field, high-cadence optical telescopes with machine learning systems trained to recognize transient patterns in real time. This would allow observatories to automatically flag events as they happen and immediately alert other telescopes to begin follow-up observations in other wavelengths. The hope is that if we can build a large enough library of events, patterns will begin to emerge. Perhaps certain types of flashes correlate with certain galactic characteristics, like black hole mass, magnetic field strength, or local star density. Or perhaps we will see recurrent behavior from a single galaxy, indicating a cyclic or repeating process. We must also consider the possibility that these transients are local to the galactic core environment. galactic centers contain not only supermassive black holes but also dense stellar populations, including old neutron stars, white dwarfs, and magnetars. If these exotic stellar remnants occasionally interact, say, through collisions, near passes, or magnetic reconnection, they could create explosive but extremely brief light events. A magnetar undergoing a starquake near the accretion disk of a black hole could send out a beam of light so intense and so fast it only lasts a millisecond before fading into the X-ray or gamma-ray background. Moreover, there could be forms of exotic matter in galactic centers that we have never observed in isolation. Strange quark matter, axion condensates, or even forms of matter that only exist in high-gravity, high-energy environments could be present. These materials might behave unpredictably, breaking down or transforming in ways that release sharp bursts of light. The core of a galaxy is the one place in the universe where the full range of known forces, gravity, electromagnetism, and the strong and weak nuclear forces, could interact at high intensity in tight spaces. That intersection might produce phenomena we can't replicate anywhere else. From a theoretical standpoint, this is where quantum gravity enters the picture. We still don't have a unified theory that connects quantum mechanics and general relativity. But the environment near a supermassive black hole is the perfect place to study this intersection. If ultrafast optical transients arise from processes involving Planck scale physics, where spacetime itself may be granular or behave as a quantum foam, then we might be glimpsing the edge of our physical models. These flashes might be the visual echo of quantum fluctuations in spacetime, amplified by the intense gravity of a black hole and projected outward like a strobe. The implications would be staggering. If UFOs are expressions of Planck-scale phenomena writ large, we would have in them the first optical evidence of quantum gravitational effects. And with the right instrumentation, we could begin probing this realm not just through thought experiments or theoretical math, but through real, observable data. Still, for now, the mystery persists. Each flash is a spark from an unseen fire. A call from a distant engine that we have not yet approached. But we are listening. And with each new detection, the signal becomes clearer. There's also a cultural and psychological dimension to this search. Throughout human history, sudden lights in the sky have inspired awe, fear, myths, and revolutions in understanding. Comets, meteors, supernovae, each reshaped the way ancient peoples viewed the heavens. In a modern sense, ultrafast optical transients play a similar role. They remind us that the sky is not static. That discovery is still possible. That mystery still exists even in an age of digital maps and catalogued galaxies. As more UFOs are detected, naming conventions may become necessary. Classification systems might emerge, just like we did with GRBs and supernovae. Perhaps we'll find UOTI and UOT2 types based on duration, brightness, decay profile, or spectral content. Entire subfields of astrophysics could emerge to study nothing but these flashes and the environments that give birth to them. Education and outreach will also play a role. These events offer a stunning visual metaphor for the unexpected power of the universe. A brief flicker of light, emerging from the heart of a galaxy, traveling across billions of light years, reaching our planet and our instruments in the blink of an eye. It's a poetic image, and one that could inspire a new generation of physicists, astronomers, and explorers. And what if, in some distant future, we find a practical use for these transients? Could they serve as cosmic timing beacons, allowing ultra-precise synchronization across interstellar distances? Could civilizations use them to coordinate activity over galactic scales, like pulses in a shared biological system? Or might they be harnessed to study the properties of intergalactic space, as their brief light passes through cosmic voids and filaments, refracting and scattering in ways that tell us more about the structure of the cosmos? None of these ideas are beyond the realm of imagination. The universe has always turned out to be more strange, more complex, and more wondrous than we expect. And perhaps most astonishing of all is the realization that these events may not be rare. The only reason they seemed elusive until now is because they were simply too fast for us to notice. If we compare this to human history, It's as if we'd been studying nature in slow motion for centuries and have only now developed the shutter speed necessary to glimpse the true tempo of the cosmos. Ultrafast optical transients could be happening constantly, hundreds, even thousands of times every second, across the observable universe, and we are only now tuning into that channel of reality. The ramifications of this are profound. If the cosmos contains an entire layer of activity happening at timescales previously invisible to us, then it implies that our understanding of astrophysical energy distribution, event frequency, and even cosmic chronology may be biased. We've been watching the slow dance of galaxies while missing the flickering strobe lights in the background. But now, with the emergence of next-generation optical detectors capable of millisecond or even microsecond resolution, the strobe is finally coming into view. This also introduces a new methodological imperative. We must redefine what it means to observe. Traditional astrophysics has relied on long exposures, averaged light curves, and days or years-long monitoring campaigns. Ultrafast optical astronomy turns that model on its head. Here, data must be collected in bursts, processed in near real time, and filtered through sophisticated algorithms capable of recognizing patterns we're not even sure exist yet. We are transitioning from a passive gaze into the sky to a reflexive, dynamic interaction with it. And what we might find as we refine this new observational paradigm could expand our concept of time itself. Already, physicists speculate about quantum time, the idea that time may not be a smooth, continuous flow but instead consist of discrete units at the Planck scale. If so, then perhaps these bursts are not just products of physical processes, but signatures of a deeper temporal lattice. Each pulse may be a resonance, a visible beat within the invisible symphony of spacetime's architecture. Some theorists are beginning to ask provocative questions. Could these ultra-fast transients be caused not by astrophysical events per se, but by fluctuations in the structure of the vacuum? That is, could the very fabric of space occasionally experience a rapid, localized shift, perhaps a kind of topological defect or quantum twitch, that manifests as a release of energy in optical frequencies? It would be the ultimate minimalist explosion, the cosmos flinching for a fraction of a second, and in doing so, illuminating itself briefly. Such ideas reside at the bleeding edge of theoretical physics, but so did the notion of gravitational waves, dark energy, and cosmic inflation before observations made them mainstream. History has shown that when new instruments reveal new layers of the universe, our understanding undergoes a seismic shift. The telescope transformed Earth-centric cosmology. The spectroscope uncovered the chemistry of stars. The particle accelerator revealed a subatomic universe. And perhaps ultrafast optical detectors will show us that the cosmos itself is twitching, flickering, and pulsating on scales we've never known. And while all of this stretches the bounds of imagination and theory, we must also remain vigilant in applying rigorous data analysis to ensure we're not being misled by instrumentation artifacts or background noise. One of the great challenges in ultrafast photometry is distinguishing real astrophysical events from spurious detections caused by cosmic rays, sensor readout errors, or algorithmic misclassification. False positives are frequent when hunting at the edge of detectability, and separating the signal from the noise requires careful cross-correlation with other instruments and telescopes. Collaborations between observatories, both ground-based and space-based, are therefore becoming crucial. Facilities like the Vera Rubin Observatory, which specializes in rapid sky surveys, and space telescopes with precise time resolution capabilities may work in tandem. Additionally, radio, X-ray, and gamma-ray counterparts can help triangulate the nature of these events. Only with such global coordination can we hope to peel back the layers and understand whether these optical transients are truly solitary events, or merely one piece of a multi-frequency phenomenon. It is also worth pondering whether the emergence of these discoveries is itself a product of evolutionary timing. Humanity's technological capabilities have grown exponentially in the past few decades. A century ago, we didn't even know other galaxies existed. Now we can detect pulses of light 1,000 times faster than the blink of an eye coming from billions of light years away. And as our technological civilization matures, we are starting to access the high-speed layer of the universe, one that has always been there, waiting for minds quick enough to perceive it. In this context, the UFOs from galactic centers serve as an invitation. They are a call to expand our vision, not just in sensitivity or wavelength, but in tempo. To shift from the slow-breathing rhythm of stars and galaxies to the heart-racing, almost quantum-like beat of transients. If traditional astronomy is a study of constellations, perhaps this new mode will be more like listening to the Morse code of the cosmos, brief, bright, and rich in hidden meaning. We must also prepare for the possibility that these events will never fully resolve into a singular cause. The universe is under no obligation to be simple. Just as supernovae come in multiple types with various origins, ultrafast optical transients may arise from a whole suite of causes: collapsing magnetars, merging black holes, quantum field interactions, cosmic strings, exotic stellar remnants, or something else entirely. The key will lie in pattern recognition, in building a taxonomy of the transients we see and correlating them with contextual data. Eventually, we may speak of Type A UFOs, Type B UFOs, or even hybrid bursts that defy existing classifications. In the long term, one could even imagine dedicated UFO observatories, equipped with fast-timing photometers, machine learning triage systems, and automated sky-scanning algorithms designed specifically for this purpose. They would act like cosmic cardiologists, listening not to the steady pulse of the stars but to the skipped beats, the sudden jolts, the cosmic palpitations that hint at deeper mysteries. The philosophical implications are no less immense. For centuries, we have looked to the heavens for constancy and order. The stars seem to represent permanence, a celestial backdrop against which human drama played out. But ultra-fast optical transients turn that notion on its head. They are not the steady glow of eternal stars, but the erratic, unpredictable sparks of something deeper. They remind us that the universe is not a silent cathedral but a dynamic, flickering theater, always moving, always mutating, always bursting into surprise. If this is the case, then maybe the most profound discovery isn't in the bursts themselves, but in what they represent: a universe that is not done speaking, a cosmos that still has secrets to tell, and a human species, fragile and limited, that dares to listen faster. And in that listening, a transformation begins, not just of our data, but of our identity as observers. For what does it mean to be an intelligent species in a universe that pulses and flares with messages we're only beginning to decipher? We often define intelligence as pattern recognition, the ability to spot signals within chaos. Ultrafast optical transients could be our latest test in that definition, a challenge issued by the cosmos itself to see whether we are perceptive enough to notice the briefest heartbeat in its vast body. As more detections accumulate and patterns emerge, we may also discover temporal clustering, instances where multiple ultra-fast transients occur in rapid succession from a single galactic nucleus. If confirmed, this would hint at coordinated or cascading events, possibly tied to cyclical phenomena near supermassive black holes. It could be an indication of orbital interactions, magnetic reconnections, or instabilities within the inner accretion disk, moments where the inner region of a galaxy hiccups in energy release, producing rapid optical flashes like flickers in a storm. Some researchers have already begun modeling how such cascades might occur. Consider, for example, a magnetically dominated region in the inner accretion zone of a black hole. Under certain pressures, magnetic field lines might tangle, stretch, and suddenly snap, a magnetic reconnection event similar to what we see in solar flares, but on a scale thousands of times more powerful. Such a release could produce a high-velocity burst of relativistic particles and radiation, resulting in an ultrafast optical flare. If multiple reconnections occurred in sequence, we could observe a chain of UFOs separated by milliseconds, like the rapid firing of neurons in a cosmic brain. But even this may not be the deepest layer of interpretation. Suppose, for a moment, that these ultra-fast transients are more than byproducts of violent events. Suppose they serve a function. Could they, in some unfathomable sense, be the result of a natural feedback mechanism in galactic evolution? Or stranger still, could they be messages? This is where we brush against the edge of what might be considered scientific speculation and philosophical wonder. After all, if a civilization advanced enough to master time domain signaling wanted to broadcast across the universe, it would make sense to do so in the fastest, most unmistakable way: brief, bright optical flashes that cut through cosmic noise like a strobe light in darkness. We already use lasers to communicate with deep space probes. A truly ancient civilization might do the same, using galactic centers as gravitational amplifiers to magnify their signal, a cosmic megaphone designed to punch through space-time. Naturally, this idea enters the realm of technosignature hunting, the scientific search for signs of technology beyond Earth. While most researchers remain cautious, it is difficult to entirely dismiss the possibility when we're seeing unexplained, high-intensity events that radiate precisely in the visible spectrum, the same band our eyes evolved to perceive. Nature, after all, doesn't favor the visible spectrum for no reason. It's the one that passes through atmosphere and dust with the most efficiency. If UFOs were artificial, it would make sense for them to exploit this window too. Still, extraordinary claims require extraordinary evidence. At present, no ultrafast optical transient has demonstrated anything clearly artificial, no repeating message, no encoded pattern, no directed origin. But even the absence of these features doesn't discount the profound natural beauty of the phenomenon. If these events are just the result of magnetar instabilities, black hole interactions, or quantum vacuum shifts, then they are still among the most energetically elegant and temporally exquisite phenomena ever observed. From an engineering standpoint, the hunt for these flashes is pushing the boundaries of what is technologically possible. New detectors must be not only fast, but extraordinarily sensitive, capable of distinguishing photons against a high-noise cosmic backdrop. Processing this data requires real-time pipelines that can compress, analyze, and interpret terabytes of information in seconds. It's an arms race between cosmic subtlety and human ingenuity. One promising technology in this race is the use of superconducting nanowire single-photon detectors, SNSPDs. These instruments can register individual photons with nanosecond precision, opening the door to detecting even shorter transients than we've yet discovered. With instruments like these deployed at high altitude, low-noise observatories, or potentially even in space, we may soon breach another boundary, the microsecond frontier. And who knows what flickers in that even faster domain? There's also the role of AI. Human astronomers simply cannot sift through billions of light curves by hand. Instead, neural networks and machine learning classifiers are being trained on known transients to recognize anomalies. These systems are particularly adept at spotting things that deviate from the norm, even if we don't yet understand why. With such systems acting as gatekeepers, flagging candidate UFOs in real time, we can dramatically increase our detection rates and push the boundaries of discovery further and faster. And as with all cosmic mysteries, the final answers will likely involve interdisciplinary insight. Understanding ultrafast optical transients will require collaboration between observational astronomers, theoretical physicists, computational scientists, and even philosophers of science. We may need new physical theories that unify electromagnetism with quantum gravity. We may need entirely new statistical models for understanding time-structured noise in the universe. And we may need new ways of thinking about light, not just as illumination, but as instantaneous transformation. The fact that these bursts come from galactic centers is no coincidence. These regions are, after all, the hearts of galaxies, places of creation and destruction, turbulence and stability, order and chaos. They are the places where the gravitational wells are deepest, where the laws of physics are pushed to their limits, and where space-time itself may buckle under the weight of mass and energy. That these centers pulse with sudden light is a poetic affirmation of the dynamic universe we inhabit, a universe that, even at its core, is alive with unpredictable change. In the coming decades, the field of ultrafast transient astronomy may evolve from a speculative niche to a foundational pillar of astrophysics. Courses will be taught, observatories will be built, and conferences will be held on the topic. Just as the study of gravitational waves has become a thriving discipline after the first detection, the same may happen for ultrafast optical phenomena. And perhaps, decades from now, we will look back at this moment as a turning point, when we began to understand that the universe does not only speak in long silences and ancient echoes, but also in flashes of brilliance, in cosmic whispers that race across the void at the speed of light, calling out to anyone fast enough to hear. As we continue to refine our instruments and expand our observational networks, the data we gather from ultrafast optical transients will inevitably accumulate into a massive archive, an unprecedented time-lapse record of the universe's fleeting illuminations. Within this treasure trove, patterns yet unseen may emerge, revealing underlying laws or even new physical principles. One particularly intriguing avenue of research involves the possibility that these ultrafast bursts might be linked to dark matter interactions. Dark matter, the mysterious substance that constitutes about 27% of the universe's mass energy content, remains invisible except for its gravitational effects. Some theories propose that dark matter particles could occasionally annihilate or decay, producing bursts of energy in the electromagnetic spectrum, including optical wavelengths. Could some of the ultrafast optical transients be signatures of such elusive processes? If this were the case, detecting and analyzing these signals would open a new window into the shadowy realm of dark matter physics, potentially solving one of the most enduring cosmic puzzles. It would be akin to finding fingerprints at a crime scene that, until now, had only whispered in the dark. Moreover, the spatial distribution of these transients offers clues. Many originate from galactic centers, but some have been observed from less active regions. Mapping the frequency and energy of bursts across different galactic environments may help determine whether their sources are linked to specific astrophysical phenomena, such as supermassive black holes, neutron stars, or exotic cosmic objects, or whether they are more uniformly spread, hinting at more fundamental, perhaps particle physics-based, origins. Another question driving the field is how these ultrafast bursts interact with their surroundings. Do they trigger cascading effects, like shockwaves propagating through interstellar gas? Do they influence star formation or galactic evolution in subtle ways? Although these events are brief, their energy can be immense, and understanding their impact on the cosmic ecosystem could shed light on the dynamic processes shaping galaxies over millions of years. Looking beyond our galaxy, the detection of ultrafast optical transients from distant galaxies also offers a powerful new tool for cosmology. Because these bursts occur on such short timescales, they can be used as precise cosmic clocks, helping to measure distances, expansion rates, and the structure of space-time. Combined with other cosmological probes, they might refine our understanding of dark energy and the universe's accelerating expansion. As we stand on the brink of this new observational frontier, it is humbling to reflect on how far we have come. From Galileo's first telescope to today's ultrafast photometers, each technological leap has expanded the canvas of our cosmic knowledge. And now, with the discovery of ultrafast optical transients, we are seeing the universe in a new dimension, one where time itself is fractured into blinks and flashes. The mystery of these transient flashes, these cosmic pulses, remains one of the most thrilling challenges in modern astrophysics. They beckon us to keep watching, keep listening, and keep questioning. Because in the heartbeats of galaxies, in the fleeting glimmers of light too swift for the eye, lies the potential to rewrite our story in the stars. As the pursuit of ultrafast optical transients intensifies, new technological innovations are emerging to meet the challenge. Adaptive optics, which correct for atmospheric distortion in real time, are becoming integral to ground-based telescopes focused on capturing these fleeting bursts. By sharpening the image quality and reducing noise, adaptive optics enhance the detection sensitivity, allowing astronomers to peer deeper into the turbulent centers of distant galaxies. Parallel to this, space-based observatories are being designed with dedicated fast-timing photometry instruments. Free from Earth's atmospheric interference, these satellites can monitor the sky continuously and detect ultrafast events without interruption. Such missions promise to increase detection rates dramatically, unveiling a fuller picture of the universe's fast-paced phenomena. International collaboration plays a pivotal role as well. Networks of telescopes spread across the globe, synchronized to observe the same regions simultaneously, enable triangulation of transient locations with unprecedented precision. This global approach also mitigates the limitations imposed by weather or daylight at any single site, ensuring a nearly constant vigil on the sky. One of the greatest advances in recent years has been the application of artificial intelligence to transient astronomy. Machine learning algorithms are now capable of analyzing vast datasets, quickly filtering out false positives, and identifying genuine ultrafast optical transient candidates. These AI systems are trained on known astrophysical events and can even flag anomalies that defy current classification, potentially leading to the discovery of entirely new types of cosmic phenomena. These tools not only increase the speed and accuracy of detection but also help in classifying the events based on their light curve shapes, spectral characteristics, and temporal patterns. As a result, researchers are beginning to assemble a taxonomy of ultrafast optical transients, grouping them by probable origin and physical mechanism. This systematic approach is crucial for transforming raw observations into meaningful scientific insight. While the astrophysical origin of many ultrafast optical transients is still under debate, some proposed sources include the merger of compact objects such as neutron stars or black holes, the sudden magnetic reconnection events in highly magnetized neutron stars called magnetars, and the rapid accretion episodes onto supermassive black holes. Each of these scenarios carries unique signatures and energetic profiles that researchers seek to distinguish through multi-wavelength observations and timing analyses. In addition to these violent events, more exotic explanations have been proposed. Hypothetical phenomena such as the interaction of cosmic strings, one-dimensional defects in spacetime predicted by some theories of the early universe, or the decay of primordial black holes could produce ultrafast bursts of light. While purely speculative at this stage, such possibilities excite both astrophysicists and particle physicists, as they hint at physics beyond the standard model. The study of ultrafast optical transients also intersects with the emerging field of multi-messenger astronomy. By combining data from electromagnetic observations with gravitational waves, neutrinos, and cosmic rays, scientists gain a holistic view of cataclysmic cosmic events. For example, the merger of two neutron stars produces not only a gravitational wave signal but also a short gamma-ray burst and, potentially, ultra-fast optical flashes. Coordinated detection across these channels can provide a detailed timeline of the event, offering insights impossible to obtain through any single messenger alone. As detection capabilities improve, we may also learn how these ultrafast bursts influence their cosmic environments. For instance, their intense energy output could accelerate particles to near-light speeds, contributing to the population of cosmic rays that bombard Earth. They might also trigger chemical reactions in surrounding gas clouds, influencing star and planet formation. Understanding these effects will deepen our appreciation of how even the briefest flashes can have lasting impacts on galactic evolution. On a philosophical level, the discovery of ultrafast optical transients challenges our perceptions of the universe's tempo. We often conceive of cosmic processes as slow and majestic, unfolding over millions or billions of years. Yet here is a realm of phenomena occurring in milliseconds or less, fast enough to escape casual notice, but powerful enough to reshape entire regions of space. This duality, the coexistence of slow, grand scales with rapid, fleeting events, speaks to the complexity of the cosmos. It suggests that understanding the universe requires not only looking outward but also tuning into its rhythm, its pulse, and its fleeting signals. Ultrafast optical transients invite us to become cosmic listeners, attuned to the briefest and brightest whispers in the vast dark. The future of this field is bright. As new instruments come online and data pours in, astronomers will continue piecing together the story behind these flashes. Whether their origins lie in the death throes of stars, the quirks of spacetime, or signals from distant civilizations, ultrafast optical transients stand as a frontier of discovery, a testament to humanity's relentless curiosity and ever-growing ability to perceive the universe in all its complexity and speed. In embracing this frontier, we affirm a profound truth: the universe is alive with mysteries waiting to be unraveled, not just in its vastness, but in the ephemeral, the instantaneous, and the ultrafast. The journey to decode ultrafast optical transients is more than just an astrophysical pursuit. It is a journey into the very nature of light, time, and existence itself. Each brief flash is a fragment of a cosmic narrative, a message encoded in photons racing across billions of light years, challenging us to listen, to interpret, and to understand. As we look forward, the potential for new discoveries related to ultra-fast optical transients extends beyond just observing them. Experimental physicists are exploring laboratory analogs, recreating conditions similar to those near black holes and neutron stars using ultra-intense lasers and plasma confinement. These experiments aim to reproduce, on a miniature scale, the mechanisms that might produce such rapid bursts of light. Such efforts could illuminate the physics behind ultra-fast transient generation and help validate theoretical models. In tandem, advances in quantum optics and photonics may offer new tools for detecting and characterizing these transients. Quantum-enhanced sensors, capable of surpassing classical limits in sensitivity and timing precision, could one day allow us to detect even fainter and faster events, pushing the boundaries of observation further into the unknown. The very act of chasing ultra-fast optical transients forces us to rethink our approach to time in astronomy. Traditional observations often integrate light over seconds, minutes, or hours, averaging out the rapid flickers of cosmic phenomena. But to capture events that last mere microseconds, if not less, requires a fundamental shift. Instruments must be designed not only to capture images but to record the flow of photons as a dynamic, high-resolution time series. This shift toward high-time resolution astronomy is transformative. It turns our telescopes into cosmic chronometers, instruments that measure the fleeting heartbeat of the universe. It may reveal new classes of phenomena, currently invisible to us, hiding in the fabric of space-time. The implications of mastering this new observational domain are profound. We may discover previously unknown transient phenomena that challenge existing astrophysical theories, or even the laws of physics as we know them. Discoveries might include ultrafast flares from exotic matter states, glimpses of quantum gravitational effects, or evidence of unknown fundamental particles interacting with electromagnetic fields. Moreover, as we refine our understanding of ultrafast optical transients, these flashes could become practical tools. For example, they might be used as natural cosmic lighthouses for navigation and timing across interstellar distances. Future space missions might harness these bursts as precise temporal markers, enabling spacecraft to navigate the galaxy with unprecedented accuracy. There is also the tantalizing possibility that these ultra-fast bursts could serve as carriers of information. If any extraterrestrial intelligence exists and seeks to communicate, brief, intense optical pulses would be an efficient way to send messages across the cosmos. Unlike continuous signals that can be lost in noise, ultra-fast bursts stand out starkly against the dark sky. Detecting such artificially generated transients would revolutionize our understanding of our place in the universe. While we have yet to find definitive evidence of such messages, the search itself expands the scope of our scientific inquiry, pushing us to develop more sensitive, faster, and smarter instruments and analysis techniques. The story of ultrafast optical transients is still in its earliest chapters, a tale being written in the light that barely flickers before vanishing. It is a story of extremes of speed, energy, and the boundaries of human perception. It is a story that brings us closer to the violent, beautiful, and mysterious hearts of galaxies and compels us to confront the unknown. As we stand under the night sky, with eyes turned toward the depths of space, the flashes of ultrafast optical transients remind us that the universe is not silent. It speaks in moments and blazes, in pulses too quick for us to see unaided, yet filled with stories and secrets waiting to be told. Our task is to listen, to build the instruments, refine the techniques, and cultivate the curiosity necessary to hear these cosmic whispers. For in doing so, we deepen our connection with the universe and move closer to answering some of the most profound questions humanity has ever asked. What is the nature of reality at its most fundamental? How do the laws of physics play out in the most extreme environments? Are we alone in this vast, pulsing cosmos, or are these flashes signs of other minds reaching across the void? Ultrafast optical transients are a beacon of possibility, a call to exploration, and an invitation to wonder. And as we continue this quest, each moment of discovery will illuminate not only the universe around us but also the boundless potential of human knowledge and imagination. The pursuit of ultrafast optical transients has sparked a renaissance in astrophysics, urging us to rethink long-held assumptions about cosmic phenomena. Traditional astrophysical processes often unfold on timescales ranging from seconds to millions of years, yet these ultrafast events challenge our understanding by occurring in milliseconds, microseconds, or even nanoseconds. This demands not only cutting-edge observational technology, but also fresh theoretical frameworks to explain their origin and behavior. One fascinating aspect is how these fleeting bursts might relate to the extreme physics near supermassive black holes. The environments around these gravitational behemoths are incredibly energetic, where gas and dust swirl at near-light speeds, magnetic fields twist and snap, and space-time itself is curved to its limits. In such settings, instabilities or sudden reconnections in magnetic fields could generate bursts of light so brief and intense they register as ultrafast optical transients. Furthermore, the interaction between relativistic jets, narrow streams of charged particles ejected from black holes, and surrounding material might also give rise to such transient flashes. When these jets collide with dense clouds or shocks in the interstellar medium, they could produce sudden bursts of electromagnetic radiation across multiple wavelengths, including optical. Understanding these processes could illuminate the role jets play in shaping galactic evolution and regulating star formation. Another promising candidate for generating ultrafast optical transients lies in neutron stars, especially magnetars. These exotic remnants of supernova explosions possess magnetic fields trillions of times stronger than Earth's, and their magnetospheres are sites of violent magnetic reconnections and crustal fractures. Such events can release enormous energy on sub-second timescales, producing bursts of X-rays, gamma rays, and potentially ultrafast optical pulses. Pinpointing these bursts from magnetars helps probe the behavior of matter under extreme magnetic stresses and densities unreachable in laboratories. Theoretical models also consider the role of binary mergers, collisions between two compact objects such as neutron stars or black holes. These catastrophic events produce gravitational waves, gamma-ray bursts, and possibly ultrafast optical flashes. Coordinated observations across gravitational and electromagnetic spectra have already transformed astrophysics, as exemplified by the detection of the neutron star merger GW170817. Future detections may uncover more transient signals, helping us understand the complex physics of mergers and the synthesis of heavy elements in the universe. In addition to known astrophysical processes, more speculative scenarios are under active investigation. Cosmic strings, hypothetical one-dimensional topological defects formed in the early universe, could produce bursts of energy when they oscillate or intersect. If such events occur, they might manifest as ultrafast optical transients, offering a rare glimpse into the physics of the universe's infancy and the unification of forces. Primordial black holes, another speculative but captivating idea, could also be a source. These black holes, formed shortly after the Big Bang, might evaporate via Hawking radiation, releasing bursts of energy that appear as ultrafast transients. Detection of such signals would have profound implications for cosmology, dark matter, and quantum gravity. The spatial distribution and frequency of ultrafast optical transients also raise intriguing questions about the large-scale structure of the universe. Some researchers speculate that these bursts might trace regions of enhanced dark matter density or align with filamentary structures of the cosmic web. By mapping their occurrence, we might better understand how visible and dark matter interact and evolve over cosmic time. Beyond astrophysics, ultrafast optical transient research intersects with quantum physics. The extreme conditions near their sources challenge our understanding of quantum electrodynamics, QED, in strong fields. Observing how light behaves in these regimes could reveal subtle effects predicted by theory, such as vacuum birefringence or photon-photon scattering, thereby testing fundamental physics. On a practical level, the hunt for ultrafast optical transients is driving innovation in detector technology. Photon counting detectors with sub-nanosecond time resolution are being developed, enabling astronomers to capture even the most fleeting bursts. These detectors, combined with high-speed data acquisition systems, generate massive datasets requiring advanced computing and machine learning techniques for analysis. Such advances have ripple effects beyond astrophysics. The technologies and algorithms devised to detect ultra-fast events inspire developments in telecommunications, medical imaging, and quantum computing. Thus, the quest to understand these cosmic flashes is fueling progress across science and technology. Moreover, the cultural and philosophical significance of ultrafast optical transients cannot be overlooked. They remind us that the universe is not a static tableau but a dynamic arena of sudden changes and ephemeral phenomena. This awareness challenges human perceptions rooted in everyday timescales and encourages us to embrace a broader temporal perspective. These fleeting bursts also evoke a sense of cosmic wonder. The idea that galaxies billions of light-years away flash in brilliant, brief pulses invisible to our unaided eyes stirs the imagination and fuels a sense of connection with the cosmos. It underscores how much there still is to discover, even in the light that reaches us every night. Looking forward, plan next-generation telescopes such as the Extremely Large Telescope, ELT, and space missions like the James Webb Space Telescope, JWST, will enhance our ability to study transient phenomena. Although primarily designed for other purposes, their sensitivity and resolution might serendipitously reveal new classes of ultrafast optical transients, or provide complementary data on known events. Additionally, proposed missions focused explicitly on time-domain astronomy, such as the Transient High-Energy Sky and Early Universe Surveyor, Theseus, aim to survey the sky for transient high-energy phenomena. While focusing on gamma rays and X-rays, these missions will synergize with optical observatories to provide comprehensive coverage of ultrafast events. The integration of data from multiple observatories, wavelengths, and messengers will be critical. As the field grows, international data-sharing platforms and collaborative networks will enable rapid follow-up and multi-wavelength characterization of detected transients, maximizing scientific return. Educational outreach and citizen science initiatives are also blossoming in this domain. Amateur astronomers equipped with sensitive cameras can contribute to transient detections, while citizen scientists help sift through data to identify candidates. This democratization of discovery engages the public and fosters a deeper appreciation for science. Ultrafast optical transients stand at the frontier of modern astronomy, bridging astrophysics, cosmology, quantum physics, and technology. They challenge us to rethink the nature of time and light, to develop new tools and theories, and to embrace the dynamic universe in all its fleeting glory. Their study promises not only to solve long-standing cosmic mysteries but also to open new horizons of discovery, expanding humanity's cosmic vision into realms once thought beyond reach. The enigma of ultrafast optical transients also poses profound questions about the limitations of human observation and understanding. Our sensory apparatus, evolved over millions of years on Earth, is attuned to timescales and energy ranges typical of our everyday environment. Yet, the universe operates across an astonishing spectrum, from the imperceptibly small and fast to the unimaginably vast and slow. Ultrafast optical transients lie far outside ordinary experience, reminding us that much of reality may be happening in flashes too brief for us to naturally perceive. This realization has inspired the development of novel observational strategies, where technology acts as an extension of human senses. Instruments capable of capturing sub-millisecond events transform our telescopes into cosmic cameras with extreme shutter speeds. But capturing these fleeting signals is only the first step. Interpreting them demands new frameworks, bridging astrophysics, particle physics, and information theory. One of the major hurdles in studying ultrafast transients is their unpredictability and rarity. Unlike periodic or long-lasting phenomena, these bursts appear suddenly, often without warning, and vanish before follow-up observations can be made. This requires astronomers to monitor vast portions of the sky continuously, with instruments that combine wide field of view and ultrafast time resolution, a formidable technical challenge. Consequently, observatories are increasingly adopting survey modes that trade spatial resolution for temporal coverage, scanning large sky areas at rapid cadence. Examples include the Zwicky Transit Facility, CTF, and the Vera-C. Rubin Observatory's Legacy Survey of Space and Time, LSST, which are revolutionizing time-domain astronomy. Though primarily designed for slower transients, their data has the potential to uncover faster events as well. Simultaneously, specialized instruments dedicated to fast photometry, such as the high-speed optical cameras mounted on large telescopes, allow detailed follow-up of candidate transients. These observations can dissect the light curves of ultra-fast events, revealing substructure and evolution on microsecond scales, crucial for distinguishing between competing physical models. Complementing optical observations, multi-wavelength campaigns incorporate radio, X-ray, and gamma-ray telescopes. Some ultra-fast transients emit across these bands, while others may be confined to optical or near-infrared. The full electromagnetic spectrum offers a comprehensive diagnostic tool, uncovering clues about emission mechanisms, surrounding environments, and energetic processes. Beyond photons, the search extends to gravitational waves and neutrinos, whose detection alongside ultra-fast optical transients can pinpoint catastrophic cosmic events like neutron star mergers or black hole disruptions. These multi-messenger observations enrich our understanding by linking disparate physical processes under a unified framework. As data accumulates, theoretical astrophysics strives to keep pace. Sophisticated numerical simulations model magnetohydrodynamics, relativistic jets, and neutron star interiors to predict signatures consistent with observed transients. These models help interpret the data and guide new observations by highlighting key diagnostic features. The challenges posed by ultra-fast optical transients have also spurred innovation in data handling and processing. The immense data rates generated by high-speed surveys necessitate real-time analysis pipelines capable of identifying interesting events instantly. Machine learning and artificial intelligence algorithms play a critical role here, enabling rapid classification and alert generation for immediate follow-up. Moreover, open data policies and collaborative platforms encourage global cooperation, fostering an environment where discoveries are rapidly shared and validated. This collaborative spirit accelerates progress and increases the likelihood of breakthroughs. Ultra-fast optical transients also invite us to consider their implications for fundamental physics. They provide natural laboratories for studying matter under conditions unattainable on Earth: ultra-high densities, extreme magnetic fields, and intense gravitational forces. Observing how light behaves in such regimes could reveal new physics or constrain theories extending beyond the standard model. The investigation of ultra-fast transients may even shed light on the nature of dark matter and dark energy. If some of these events arise from exotic particles or early universe relics, detecting and characterizing them could offer clues to these profound cosmic mysteries. On a more speculative note, the potential of ultra-fast optical transients as communication signals from advanced extraterrestrial civilizations has captivated scientists and the public alike. Their distinctive, brief, and bright nature makes them ideal candidates for intentional signaling across vast cosmic distances, escaping the noise that obscures continuous emissions. While no conclusive evidence of artificial origin has emerged, the search for technosignatures increasingly incorporates the detection of transient events, broadening the scope of the search for extraterrestrial intelligence. SETI. Culturally, ultra-fast optical transients deepen our appreciation for the dynamic and interconnected universe. They remind us that the cosmos is not merely a static backdrop but a theater of sudden, dramatic acts. Each flash is a cosmic punctuation mark, signifying a moment of transformation, energy release, or a shift in the grand cosmic narrative. Educationally, these phenomena provide compelling stories to engage the public, illustrating the interplay of fundamental physics, cutting-edge technology, and cosmic mystery. Outreach programs leverage the intrigue of ultra-fast transients to inspire future generations of scientists and engineers. Looking ahead, the field of ultra-fast optical transients is poised for explosive growth. Upcoming telescopes, advances in detector technology, and computational breakthroughs promise to unveil many more such events, transforming our understanding of the energetic universe. The synthesis of observational data, theoretical insights, and technological innovation will likely lead to a new era in time-domain astrophysics, where the ultra-fast universe becomes an accessible frontier rather than an elusive mystery. In this unfolding story, every detected burst is a clue, a message from distant corners of space and time. They challenge us to expand our scientific vision, to embrace complexity, and to remain ever curious. The study of ultrafast optical transients thus stands as a testament to human ingenuity and the insatiable quest to comprehend the universe in all its temporal richness, from the slow sweep of galaxies to the lightning-fast flashes that illuminate the cosmos's hidden corners. Ultrafast optical transients have transformed our understanding of cosmic variability, revealing a universe far more dynamic and transient than previously imagined. Before their discovery, astronomical events were generally studied on timescales spanning seconds to millennia. However, the detection of bursts lasting mere microseconds or less shatters this paradigm, opening a new temporal window through which to explore the cosmos. This new window offers tantalizing insights into phenomena at extreme scales of energy and gravity. The ultra-fast timescales suggest origins in compact, highly energetic environments, where physical conditions approach or even exceed known theoretical limits. It's a realm where matter behaves in ways that challenge classical physics, and quantum effects become significant. The potential sources of these bursts span a diverse array of exotic astrophysical objects. Among these, pulsars, rapidly spinning neutron stars with strong magnetic fields, are key suspects. Pulsars emit regular pulses of radiation, but some exhibit giant pulses that occur unpredictably and can be extraordinarily brief and intense. These giant pulses might be a form of ultrafast transient, providing clues about the complex magnetospheric processes of neutron stars. Magnetars, another type of neutron star with even stronger magnetic fields, are also prime candidates. Their occasional bursts of high-energy radiation may include brief optical flashes, revealing sudden magnetic reconnection events or crustal fractures. These extreme events illuminate the behavior of matter and magnetic fields under extraordinary conditions. Black hole environments are equally compelling. Accretion disks around supermassive black holes funnel enormous amounts of material inward, heating to extreme temperatures and generating intense magnetic fields. Instabilities or reconnection events within these disks can produce ultrafast optical bursts, serving as cosmic beacons from the galactic centers where these black holes reside. Additionally, the collisions and mergers of compact objects, such as neutron star pairs or black hole neutron star systems, offer a natural laboratory for ultrafast transient generation. These cataclysmic events release gravitational waves and energetic electromagnetic signals, sometimes including ultrafast optical flashes. Observations combining gravitational wave detectors like LIGO and Virgo with optical telescopes have already heralded a new era of multi-messenger astrophysics. Beyond known astrophysical processes, more speculative origins have been proposed. The evaporation of primordial black holes through Hawking radiation could generate intense but brief bursts of light. If detected, such signals would provide revolutionary insights into early universe conditions and quantum gravity. Cosmic strings, hypothetical defects in spacetime formed during the early universe, might also emit bursts when they oscillate or interact. Detecting ultrafast optical transients from cosmic strings would confirm their existence and inform grand unified theories. On the observational side, capturing ultrafast optical transients requires instrumentation capable of both rapid time resolution and wide sky coverage. Photodetectors with sub-nanosecond timing and sensitive optics are critical, combined with data pipelines capable of processing immense volumes of information in real time. This technological challenge has driven innovations in sensor design, such as superconducting nanowire single-photon detectors, which offer exceptional sensitivity and timing precision. Advances in fiber optics, ultra-fast electronics, and high-speed data storage further support these capabilities. The development of machine learning algorithms has revolutionized transient detection. These AI-powered tools can sift through massive datasets to identify subtle, fleeting signals amid noise, enabling rapid alerts and follow-up observations. Coordinated international networks of observatories maximize the chance of catching ultrafast transients. By sharing data and alerts globally, astronomers can mobilize resources quickly to study events before they fade. Multi-wavelength and multi-messenger approaches are crucial. Optical bursts may coincide with radio, X-ray, gamma-ray, or neutrino signals, providing a comprehensive picture of the underlying astrophysical event. The synergy of diverse observatories expands detection sensitivity and enhances interpretation. The study of ultrafast optical transients also informs fundamental physics. These bursts probe conditions where quantum electrodynamics, general relativity, and plasma physics intersect. They offer opportunities to test theoretical predictions, such as vacuum polarization effects or the behavior of matter in ultra-strong fields. Furthermore, these transients could offer clues about dark matter if some arise from interactions involving exotic particles or early universe phenomena. Observing and characterizing such events might provide indirect evidence of the dark sector's nature. The search for extraterrestrial intelligence, SETI, has embraced ultrafast optical transients as potential technosignatures. Their brief, intense nature makes them ideal for interstellar communication signals designed to be easily distinguished from natural astrophysical noise. While no definitive artificial ultrafast signals have been identified, ongoing surveys broaden the scope of SETI, integrating optical transient detection with traditional radio searches. This multidisciplinary approach enriches the quest to answer whether humanity is alone in the cosmos. Public fascination with ultrafast optical transients is growing, driven by the drama of cosmic fireworks occurring in the blink of an eye. These events capture the imagination, highlighting the universe's unpredictability and dynamism. Educational initiatives use ultrafast transients to inspire interest in physics, astronomy, and technology. Their study connects fundamental science with cutting-edge instrumentation, computational challenges, and cosmic exploration narratives. Looking ahead, the next generation of telescopes and detectors promises to deepen our understanding. Facilities like the Extremely Large Telescope, ELT, the Vera Rubin Observatory, and specialized fast photometry instruments will probe these fleeting phenomena with unprecedented sensitivity and resolution. Space-based observatories equipped with ultrafast detectors may escape atmospheric interference, providing clearer views of transient optical events. Missions like the proposed Theseus satellite aim to capture transient high-energy phenomena, complementing optical studies. The integration of gravitational wave observatories and neutrino detectors with electromagnetic telescopes will foster a holistic multi-messenger astronomy, revealing ultrafast events' full physical context. Ultrafast optical transients represent a frontier of astrophysics where time scales compress, energies peak, and mysteries abound. Their study challenges and expands our understanding of the universe's most extreme environments and fundamental physics. Each detected flash is a whisper from the cosmos's most energetic and ephemeral processes. Listening carefully, astronomers are decoding these signals, uncovering secrets that reshape our cosmic narrative and illuminate the dynamic universe in which we live. The exploration of ultrafast optical transients is a testament to human curiosity, technological ingenuity, and the enduring drive to comprehend the universe's fleeting yet profound moments. The implications of ultrafast optical transients ripple beyond astrophysics into other scientific disciplines, highlighting the interconnectedness of knowledge. For instance, understanding the physics behind these fleeting bursts enhances plasma physics, helping to model conditions relevant for nuclear fusion and laboratory astrophysics. The extreme magnetic and gravitational environments that produce ultrafast transients can be partially recreated in high-energy physics experiments, fostering cross-disciplinary collaboration. Moreover, the data handling challenges posed by transient detection have driven advancements in computer science, especially in big data processing, artificial intelligence, and real-time analytics. Techniques developed for analyzing massive, fast-changing astrophysical datasets find applications in finance, healthcare, cybersecurity, and more. This cross-pollination of ideas exemplifies how astronomy continues to push technological and methodological boundaries. The global nature of ultrafast transient research has also spurred the growth of international scientific partnerships. Observatories spanning multiple continents and space-based platforms coordinate to ensure rapid response and continuous sky coverage. Initiatives such as the global relay of observatories watching transients happen, growth, exemplify how collaborative networks can overcome the intrinsic unpredictability of these phenomena. Simultaneously, citizen science projects have empowered the public to participate in transient discovery. Platforms like Zooniverse allow enthusiasts to assist in identifying unusual light curves or optical flashes, democratizing scientific discovery and fostering broader interest in astronomy. Beyond direct detection, modeling and simulations play a pivotal role. Computational astrophysicists develop sophisticated codes to recreate the magnetohydrodynamic environments and relativistic effects thought to produce ultrafast transients. These simulations help interpret observations, test hypotheses, and predict new types of events. A notable theoretical framework involves magnetic reconnection, the process where magnetic field lines snap and realign, releasing vast amounts of energy suddenly. This mechanism, observed in the Sun's corona and Earth's magnetosphere, is thought to operate near compact objects at scales that produce ultrafast optical bursts. Understanding reconnection in extreme astrophysical settings advances plasma physics and may inform fusion research. Other models propose that sudden shifts in neutron star crusts or quakes in magnet Rs trigger rapid emission. These starquakes release pent-up stress accumulated over long periods, leading to bursts lasting microseconds or milliseconds. The resulting radiation offers a window into neutron star interior structure, composition, and equation of state. Fast radio bursts, FRBs, mysterious millisecond-long pulses at radio wavelengths, share intriguing parallels with ultrafast optical transients. Some hypotheses suggest that at least a subset of FRBs might have optical counterparts that are extremely brief and bright, motivating coordinated multi-wavelength searches. While FRBs remain enigmatic, their study enriches the understanding of transient phenomena, providing context and comparison points for optical bursts. The potential connection between different classes of transients hints at a broader taxonomy of fast cosmic events, driven by related physical processes. In addition to astrophysical research, ultrafast optical transients have practical implications for space exploration and communication technologies. Understanding rapid high-energy events helps in designing spacecraft shielding and communication protocols that can withstand or avoid interference from intense cosmic bursts. Furthermore, these transients inform astrobiology by characterizing the radiation environment around compact objects and galactic centers, regions often considered hostile to life. Assessing the frequency and intensity of such bursts aids in evaluating habitability and the distribution of life-supporting conditions across the galaxy. Philosophically, the fleeting nature of ultrafast optical transients invites reflection on time and perception. They challenge human intuition, reminding us that our experience of time is limited and that the universe unfolds in ways both grand and ephemeral. The pursuit of understanding these brief flashes embodies a deeper quest to grasp the universe's totality, its rhythms, energies, and transformations, from the momentary to the eternal. It highlights the balance between chaos and order, permanence and transience. Technological advancements in quantum optics and photonics may also benefit from insights gained studying ultrafast transients. The mechanisms that produce and modulate light on microsecond or shorter timescales parallel developments in quantum communication and computing. In this way, cosmic phenomena inspire and accelerate innovation on Earth, blurring the line between fundamental research and applied science. Looking forward, the synergy between theoretical predictions and observational breakthroughs will continue to drive the field. As new ultrafast events are discovered, refined models will emerge, elucidating the physical conditions that give rise to them. Planned missions like the Large Synoptic Survey Telescope, LSST, and space observatories with ultrafast photometric capabilities will dramatically increase the rate of transient discoveries. These facilities will uncover patterns, populations, and perhaps entirely new classes of ultrafast phenomena. With each discovery, the catalog of ultrafast optical transients will grow, providing statistical samples sufficient for population studies. This will enable astronomers to map their occurrence rates, energy distributions, and spatial distributions across different galactic environments. Such knowledge will clarify the life cycles of compact objects, the evolution of magnetic fields, and the role of transient energetic events in galaxy dynamics. Ultimately, ultrafast optical transients exemplify the universe's capacity for surprise. They beckon us to look deeper, listen closer, and think faster. They demonstrate that the cosmos is a place of rapid change and profound mystery, where moments that last less than the blink of an eye carry the weight of cosmic history and physics at its most extreme. For humanity, studying these fleeting bursts is both a scientific challenge and a poetic journey, a quest to understand the briefest sparks of cosmic light that punctuate the vast darkness, signaling events that shape the universe itself. The exploration of ultrafast optical transients not only challenges our scientific tools but also reshapes the philosophical framework through which we view the cosmos. The ephemeral nature of these bursts underscores the transient character of many cosmic processes, highlighting that the universe is not a static tableau but an ever-evolving tapestry woven with moments of extraordinary brilliance that vanish almost as quickly as they appear. This realization invites us to reconsider our place in the cosmos, not as observers of a fixed reality, but as participants in an unfolding cosmic drama where the flow of time and change is paramount. In practical terms, the detection of ultrafast optical transients necessitates innovations in both instrumentation and data analysis. Traditional astronomical observations, often optimized for long exposures to capture faint, steady sources, must be complemented with ultra-high-speed photometry and time tagging capable of resolving events on microsecond or nanosecond scales. The integration of single-photon detectors, capable of registering individual photons with precise timing, has been a major breakthrough, enabling astronomers to capture the delicate flickers of these fast transients. The data volumes generated by high-cadence surveys and fast photometry instruments are enormous, requiring sophisticated algorithms for real-time data processing, filtering, and event classification. Machine learning methods have been instrumental in managing this data deluge, efficiently distinguishing genuine cosmic signals from noise and terrestrial interference. These AI-driven techniques evolve continuously, adapting to new data patterns and expanding the discovery potential. The transient sky is crowded with a menagerie of events spanning a wide range of timescales and energies, from slow-evolving supernovae to millisecond bursts, and now to ultra-fast optical transients that push the limits of detectability. Distinguishing these fast transients from instrumental artifacts and atmospheric phenomena is a complex task, demanding rigorous calibration and verification procedures, as well as coordinated multi-observatory campaigns. One of the more compelling avenues for understanding ultra-fast optical transients lies in multi-messenger astronomy. The coordination of electromagnetic observations with gravitational wave detectors like LIGO, Virgo, and CAGRA has already transformed astrophysics. For example, the 2017 detection of a neutron star merger through both gravitational waves and electromagnetic signals heralded a new era of discovery. Ultrafast optical bursts may similarly coincide with or precede gravitational wave events, offering early warning and insight into the violent processes involved. Neutrino observatories such as IceCube add another dimension, potentially linking ultrafast optical transients to high-energy neutrino emissions from cosmic accelerators. If connections between these messengers are established, they will unlock unprecedented understanding of particle acceleration and matter interactions in extreme environments. From a theoretical standpoint, the challenge is to reconcile the observed ultrafast optical transients with existing models of compact object physics, magnetohydrodynamics, and high-energy particle interactions. This has led to vigorous research into phenomena such as relativistic shocks, magnetic reconnection layers, and quantum electrodynamic effects under strong fields. The interplay of these processes at sub-millisecond timescales remains a frontier of astrophysical theory. Ultrafast optical transients are also reshaping our understanding of galactic centers, which are often home to supermassive black holes surrounded by dense star clusters and turbulent gas. These environments are natural laboratories for extreme physics, where ultrafast bursts may originate from accretion instabilities, tidal disruptions of stars, or interactions with compact objects. The detection of these bursts helps map the dynamics and energetic processes occurring near these enigmatic cosmic engines. The search for ultrafast optical transients is not confined to optical wavelengths alone. There is increasing interest in exploring the near-infrared, ultraviolet, and even X-ray regimes for analogous fast transients. Each wavelength band probes different physical conditions and emission mechanisms, enriching the overall picture and potentially uncovering new phenomena. In terms of cosmic timescales, ultrafast transients may also provide clues about the early universe. Some theorists speculate that primordial black holes or exotic matter phases from the Big Bang epoch could emit ultrafast bursts, giving us a glimpse into conditions billions of years ago. Detecting such signals would revolutionize cosmology, opening a window into the universe's infancy. The potential role of ultrafast optical transients as communication signals has invigorated the SETI community. Unlike traditional continuous signals, brief optical flashes can traverse interstellar distances efficiently, with lower energy requirements and less susceptibility to interference. Searches for such signals employ rapid photometric monitoring of nearby stars and galactic centers, aiming to detect patterns or repeated bursts that might indicate artificial origin. While no confirmed extraterrestrial signals have been detected, the methodologies developed for transient detection enhance the overall sensitivity of searches, ensuring that we are prepared should such a signal ever appear. Ultrafast optical transients also intersect with astrobiology. Understanding the frequency and intensity of high-energy bursts in various galactic environments informs models of habitability and the potential impact on biospheres. Intense bursts could sterilize planetary surfaces or disrupt atmospheres, influencing the development and sustainability of life. The cultural and educational impact of studying ultrafast optical transients is profound. They serve as compelling examples of the dynamic, ever-changing universe, capturing public imagination and inspiring interest in science and technology. Educational programs leverage their mystery and excitement to motivate students and the public towards STEM fields. As research advances, new discoveries of ultrafast optical transients are likely to challenge existing classifications and force revisions of astrophysical theory. The rich diversity of sources and mechanisms suggests a continuum of phenomena, blurring boundaries between known categories such as pulsars, magnetars, fast radio bursts, and newly emerging transient classes. Ultimately, the study of ultrafast optical transients exemplifies the spirit of exploration. It demands pushing technological limits, fostering interdisciplinary collaboration, and maintaining openness to unexpected findings. These brief cosmic flashes, though fleeting, hold profound secrets about the universe's most extreme environments and fundamental processes. Every ultrafast optical transient detected enriches our cosmic narrative, revealing the universe not only as a vast expanse of space but as a stage for extraordinary events unfolding in the blink of an eye. The landscape of ultrafast optical transient research continues to evolve rapidly, driven by both theoretical breakthroughs and technological advancements. One promising frontier is the integration of quantum technologies into astrophysical instrumentation. Quantum detectors, employing principles such as entanglement and squeezing, offer the potential to surpass classical sensitivity limits, enabling the detection of even fainter and briefer signals than currently possible. These advances may open new windows on transient phenomena that have so far evaded observation. Simultaneously, the rise of nanosatellites and small, agile space observatories presents exciting opportunities for ultrafast transient studies. These platforms can provide continuous monitoring with minimal atmospheric distortion, complementing large ground-based telescopes. Distributed networks of nanosatellites equipped with ultrafast photometers could achieve near-global coverage, significantly increasing detection rates and enabling precise triangulation of transient origins. The development of adaptive optics and interferometry also enhances our ability to resolve the environments around compact objects, contextualizing ultrafast bursts within their complex surroundings. High spatial resolution combined with ultrafast timing offers a multidimensional view of transient events, essential for unraveling their physical mechanisms. The interplay between magnetohydrodynamics and radiation processes at extreme energies remains an active area of theoretical investigation. Researchers are modeling the formation and evolution of magnetospheres, relativistic jets, and shock fronts to understand how energy is converted into brief optical flashes. Insights from plasma physics, informed by both astrophysical observations and laboratory experiments, drive this progress. On the observational front, time-domain astronomy is maturing into a fully fledged discipline, with ultrafast optical transients at its cutting edge. Upcoming surveys with unprecedented temporal resolution promise to unveil populations of transients that have remained hidden due to observational constraints. These surveys will refine our statistical understanding of transient event rates, luminosity functions, and spatial distributions. The characterization of these populations is critical for constructing comprehensive astrophysical models. For example, determining the frequency and energy distribution of ultrafast bursts from magnetars can elucidate their magnetic field decay and starquake activity. Similarly, mapping ultrafast bursts near supermassive black holes informs theories of accretion disk dynamics and jet launching mechanisms. Interdisciplinary collaborations play a pivotal role in this endeavor. Astronomers, physicists, computer scientists, and engineers work in concert to design experiments, develop data analysis pipelines, and interpret results. This collaborative spirit accelerates innovation and broadens the scope of inquiry. Educational programs are increasingly emphasizing the interdisciplinary nature of transient astronomy, preparing a new generation of researchers equipped to tackle its challenges. Workshops, summer schools, and online courses cover topics ranging from high-speed photometry and signal processing to plasma astrophysics and general relativity. Public engagement remains a cornerstone of the field. Outreach activities leverage the captivating nature of ultrafast transients to communicate broader scientific concepts, fostering scientific literacy and enthusiasm. Citizen science platforms invite the public to participate directly, creating a sense of shared discovery. In the realm of theoretical physics, ultrafast optical transients offer testing grounds for hypotheses involving quantum gravity and space-time structure. Some models predict that exotic phenomena, such as space-time foam or quantum fluctuations, could manifest as ultrafast variations in light emission near black holes or neutron stars. Observations of transients at the shortest timescales may provide empirical evidence supporting or refuting these ideas. Another intriguing possibility is the detection of signals related to dark matter interactions. Certain dark matter candidates, such as axions or primordial black holes, might produce brief optical bursts through decay or annihilation processes. Although speculative, searching for such signatures expands the scientific impact of transient astronomy into fundamental particle physics and cosmology. As detection techniques improve, the boundary between known astrophysical phenomena and potential new physics will blur, highlighting the exploratory nature of the field. The discovery of unexpected transient types would prompt re-evaluation of existing models and inspire new theoretical frameworks. From a cosmological perspective, ultrafast optical transients might serve as probes of the intergalactic medium and cosmic expansion. Their brief, bright flashes can be used as beacons to study intervening matter and to measure cosmological parameters with high precision. This application complements traditional standard candles and opens new avenues for observational cosmology. In terms of technological impact, advances motivated by ultrafast transient detection influence other fields, such as telecommunications, where ultrafast signal processing is crucial. The demands of high-throughput, low-latency data handling stimulate progress in photonics, electronics, and information technology. Furthermore, the challenge of detecting and analyzing ultrafast optical transients drives improvements in calibration techniques and noise reduction, benefiting a wide range of optical and radio astronomy projects. These enhancements elevate the overall quality of astronomical data and enable new scientific discoveries. The discovery of ultrafast optical transients challenges us to rethink the temporal dimension in astrophysics. Traditionally, astronomical phenomena were categorized largely by spatial scale or spectral properties. Now, time resolution emerges as a critical axis, revealing rapid processes and transient events that enrich our understanding of cosmic dynamics. This shift emphasizes that time domain and multi-messenger astronomy are inseparable, each providing complementary insights into the universe's behavior. Together, they enable a holistic exploration of astrophysical phenomena across all scales and messengers. The future of ultrafast optical transient research is bright, driven by curiosity, innovation, and a relentless quest to decipher the universe's most fleeting signals. As new generations of scientists build upon current knowledge, they will undoubtedly uncover surprises that challenge and expand our cosmic perspective. Ultrafast optical transients represent a frontier where extreme physics, cutting-edge technology, and deep cosmic mysteries converge. Their study enriches astrophysics, informs fundamental physics, and inspires humanity's enduring wonder at the cosmos. These brief cosmic flashes, fleeting though they may be, illuminate profound truths about the universe and our place within it. The quest to understand ultrafast optical transients has also led to an examination of the environments surrounding the sources of these bursts. Galactic centers, in particular, are complex regions rich in phenomena capable of producing such fleeting emissions. The dense concentration of stars, gas, dust, and dark matter near supermassive black holes creates dynamic conditions ripe for energetic outbursts. Studying ultrafast transients originating here offers unique insight into the interplay between black holes and their surroundings. The gravitational influence of a supermassive black hole profoundly affects nearby matter. Accretion disks composed of infalling gas and dust orbit these cosmic giants, heating up and emitting radiation across the electromagnetic spectrum. Instabilities in these disks can cause rapid changes in brightness, potentially contributing to some ultrafast transient events. Additionally, jets of relativistic particles emitted along magnetic field lines emanating from the black hole's poles may produce brief optical flashes as shocks propagate through the surrounding medium. Another possible source of ultrafast optical transients in galactic centers is the interaction between compact objects, such as neutron stars and stellar mass black holes, and the ambient environment. When these dense remnants pass through regions of high gas density or encounter tidal forces, they can trigger sudden energy releases manifesting as rapid optical bursts. The complex gravitational choreography of multiple objects in these crowded centers contributes to a rich transient landscape. The role of magnetic fields in these environments cannot be overstated. Galactic centers harbor some of the strongest magnetic fields observed in the universe, shaping the behavior of plasma and influencing the acceleration of particles. Magnetic reconnection events, where field lines snap and realign, release immense energy on very short timescales, potentially generating ultrafast optical transients. Understanding the precise mechanisms requires integrating data from multiple observational platforms. Radio telescopes revealed the synchrotron emission from relativistic electrons spiraling along magnetic fields, while X-ray observatories detect high-energy processes near compact objects. Optical telescopes, equipped with ultrafast detectors, capture the brief flashes that are the hallmark of ultrafast transients. Combining these data streams provides a multidimensional view, essential for decoding the physics at play. Recent observations have revealed correlations between ultrafast optical transients and high-energy gamma-ray flares in galactic centers, hinting at a shared origin. These simultaneous multi-wavelength events suggest that processes such as shock acceleration, magnetic reconnection, or sudden changes in accretion rate can produce emissions spanning the entire electromagnetic spectrum on ultrafast timescales. The detection of ultrafast optical transients from galactic centers also informs studies of galaxy evolution. Energetic feedback from black holes and transient events influence star formation, gas dynamics, and chemical enrichment. Understanding how these brief bursts fit into the broader context of galactic ecology sheds light on the coevolution of black holes and their host galaxies. Moreover, ultrafast optical transients may contribute to the diffuse background light observed across the universe. While individually brief, the cumulative effect of countless such events over cosmic history could impact measurements of cosmic background radiation, influencing cosmological models. From a methodological standpoint, pinpointing the precise locations of ultrafast optical transients within galactic centers is challenging. The high density of sources and the complexity of emission processes demand high angular resolution and precise timing. Interferometric techniques and next-generation observatories aim to overcome these hurdles, promising unprecedented clarity. The advent of extremely large telescopes, ELTs, with apertures exceeding 30 meters, will significantly enhance our ability to resolve structures in galactic centers and study transient phenomena in exquisite detail. Coupled with fast photometric instruments, these facilities will open new windows on ultrafast transient physics. Understanding ultrafast optical transients in galactic centers also has implications for gravitational wave astronomy. Compact object interactions and mergers occurring near supermassive black holes can generate gravitational waves alongside electromagnetic bursts. Coordinated observations can provide comprehensive insights into these dramatic events. The synergy between observations, theory, and simulation is crucial. Computational models simulate accretion flows, magnetic fields, and relativistic jets to reproduce observed transient behavior. These models are continually refined by new data, improving predictive power and guiding future observations. Additionally, ultrafast optical transient research is pushing the frontiers of detector technology. Innovations include superconducting nanowire single-photon detectors and ultra-low noise cameras capable of capturing photons with sub-nanosecond precision. These tools are vital for detecting and characterizing the briefest and faintest cosmic flashes. The study of ultrafast optical transients also intersects with the search for exotic astrophysical objects, such as hypothetical quark stars or dark matter clumps, which may produce unique transient signatures. Detecting such signals could confirm or constrain theories about the nature of dense matter and dark matter. In the broader astrophysical context, ultrafast optical transients challenge traditional notions of steady-state emission, revealing a universe that is more dynamic and unpredictable than previously appreciated. They underscore the importance of time-domain astronomy as a key pillar of modern astrophysics. As our observational capabilities grow, the catalog of known ultrafast transient events will expand, providing a richer dataset for statistical analysis. This will enable astronomers to discern population properties, evolutionary trends, and environmental dependencies. Ultimately, the continued exploration of ultrafast optical transients from galactic centers promises to unlock profound insights into fundamental physics, cosmic evolution, and the extreme conditions shaping our universe. These fleeting cosmic flashes illuminate the darkest, most energetic corners of galaxies, telling stories of creation, destruction, and transformation on the grandest scales imaginable. The phenomenon of ultrafast optical transients from galactic centers carries profound implications for our understanding of the life cycles of stars and the end states of stellar evolution. Within the crowded and energetic heart of galaxies, stars live out their lives under intense gravitational and radiative pressures, and many eventually collapse into compact remnants, white dwarfs, neutron stars, or black holes. These remnants, especially neutron stars and black holes, are prime suspects as progenitors of ultrafast optical transients. Neutron stars, with their incredibly dense cores and powerful magnetic fields, exhibit behaviors that might generate these rapid optical bursts. Magnet-Rs, a type of neutron star with magnetic fields trillions of times stronger than Earth's, are known to produce intense X-ray and gamma-ray flares. It is plausible that some of these flares have optical counterparts with ultrafast temporal characteristics. The mechanisms, potentially involving sudden magnetic reconnection or crustal star quakes, release energy abruptly and could produce the brief flashes observed. Black holes in galactic centers may also be key players. When material from nearby stars or gas clouds falls into the intense gravitational well of a supermassive black hole, it forms an accretion disk that can heat to extreme temperatures and generate energetic emissions. Instabilities in this accretion process, such as sudden surges in infalling matter or magnetic interactions, might cause ultrafast optical transients. The challenge lies in distinguishing these from other transient sources in the densely populated galactic core. The tidal disruption events (TDs) where a star ventures too close to a supermassive black hole and is torn apart by gravitational forces, are also associated with bursts of radiation. Though typically lasting longer than the ultrafast regime, certain phases within TDs might produce rapid optical flashes as the debris interacts dynamically near the black hole's event horizon. Another intriguing possibility involves interactions between compact objects themselves. Binary systems of neutron stars or black holes can undergo mergers, emitting gravitational waves and electromagnetic radiation. Although the primary electromagnetic signals often last seconds to minutes, precursors or post-merger phenomena might manifest as ultrafast optical transients, providing critical clues about the merger physics and environment. The detection of these ultrafast events is technologically demanding. Earth's atmosphere can distort and absorb optical signals, and terrestrial light pollution complicates observations. Space-based observatories, free from atmospheric interference, offer a strategic advantage for monitoring galactic centers for such fleeting bursts. Missions like the Hubble Space Telescope and upcoming projects like the James Webb Space Telescope, although not optimized for ultrafast timing, provide valuable complementary data. The synergy between ground-based and space-based observatories enhances temporal and spectral coverage. Coordinated campaigns involving facilities spanning radio, optical, X-ray, and gamma-ray wavelengths enable comprehensive characterization of transient events, crucial for identifying their nature. From a computational perspective, modeling the complex physics of galactic centers challenges current capabilities. Simulations must incorporate general relativity, magnetohydrodynamics, radiation transfer, and particle acceleration, all operating under extreme conditions. Advances in high-performance computing and algorithm development are critical for producing realistic models that can be tested against observations. Data analysis also involves distinguishing ultrafast optical transients from myriad noise sources and terrestrial interference. Sophisticated signal processing techniques, including wavelet analysis and machine learning classifiers, help isolate genuine astrophysical events. These tools evolve continually as new data and event types emerge. The discovery of previously unknown classes of ultrafast optical transients remains a tantalizing prospect. As surveys deepen and data volumes grow, anomalies and outliers will likely emerge, potentially revealing exotic or unexpected astrophysical processes. The importance of understanding ultrafast optical transients extends beyond astrophysics to fundamental physics. These phenomena occur in regimes of extreme gravity, density, and magnetic field strength, offering natural laboratories for testing theories of matter under conditions unattainable on Earth. For example, they provide opportunities to probe the behavior of matter at nuclear densities within neutron stars, the properties of strong field gravity near black holes, and the dynamics of relativistic jets. These insights feed back into broader questions about the nature of space, time, and fundamental forces. Moreover, the study of ultrafast optical transients intersects with quantum physics. Certain models predict that quantum effects may influence the emission processes near compact objects, particularly at the shortest timescales and highest energies. Observations can thus inform attempts to unify quantum mechanics with gravity. As observational campaigns continue, international collaborations become increasingly important. Large-scale projects require coordination among institutions across continents, sharing data, resources, and expertise. These global networks enhance the scope and depth of transient studies, fostering a vibrant scientific community. Educational outreach accompanying these efforts helps inspire new generations of scientists and raises public awareness about the dynamic universe. The dramatic nature of ultrafast optical transients, bright flashes signaling violent cosmic processes, captivates imaginations and promotes scientific literacy. Looking ahead, the integration of artificial intelligence and automation in observatories promises to revolutionize transient detection. Real-time analysis pipelines can identify ultrafast events immediately, triggering follow-up observations and maximizing scientific return. The ultimate goal is to develop a comprehensive temporal map of the universe, cataloging transient phenomena across all timescales and energies. Ultrafast optical transients represent a critical, previously elusive component of this cosmic timeline. By piecing together these rapid events, scientists aim to construct a more complete understanding of the universe's energetic processes, from the smallest scales of particle interactions to the largest scales of galaxy dynamics. Ultrafast optical transients from galactic centers embody some of the most exciting challenges and opportunities in contemporary astrophysics. They push the boundaries of technology, theory, and observation, promising profound discoveries about the cosmos. Each new detection adds to a growing tapestry of knowledge, revealing the hidden rhythms of a universe in perpetual motion, moments of intense energy flashing briefly, then vanishing, yet leaving an indelible imprint on our understanding of space and time. The investigation of ultrafast optical transients (UOTs) also demands a deep dive into the mechanisms that govern the generation and propagation of light within extreme astrophysical environments. The optical flashes we observe do not simply emanate from isolated points in space. Rather, they traverse complex and often turbulent media, which can alter their properties significantly before reaching Earth-based detectors. Intervening materials such as dust clouds, ionized gas, and magnetic fields within the galactic center can absorb, scatter, or polarize the transient's light. This interaction can change the apparent brightness, spectrum, and temporal profile of the burst. Careful modeling of these propagation effects is necessary to reconstruct the intrinsic characteristics of the ultrafast transient and to accurately infer the physical conditions at the source. One particularly important phenomenon is scattering caused by interstellar and circumnuclear dust. This can lead to light echoes, where brief bursts are scattered and delayed, producing secondary signals that can confuse time-domain analyses. Detecting and distinguishing direct ultrafast flashes from their echoes requires high temporal resolution and sophisticated data processing. Polarization measurements provide another valuable diagnostic. Light emitted by highly magnetized environments is often polarized in characteristic ways. Measuring the polarization degree and angle of ultrafast optical transients can yield clues about magnetic field orientation, strength, and geometry at the source region. Spectroscopic studies, although challenging due to the brevity of these transients, are crucial for understanding the physical processes involved. Rapid spectroscopy capable of resolving transient features on millisecond timescales can reveal emission or absorption lines that diagnose temperature, velocity, chemical composition, and ionization states of the emitting plasma. Technological advances in high-speed spectroscopy, such as integral field units with fast readout detectors, are gradually enabling such observations. These tools promise to transform our ability to dissect the physics of ultrafast optical transients in real time. Theoretical models suggest that a variety of emission mechanisms could be responsible for ultrafast optical bursts. Synchrotron emission, produced when relativistic electrons spiral around magnetic field lines, is a common candidate in high-energy astrophysics. The rapid acceleration of electrons during magnetic reconnection events or shock fronts could generate brief, intense optical synchrotron flashes. Alternatively, thermal emission from hot plasma heated suddenly by shock compression or magnetic dissipation may contribute to the optical transient. In some scenarios, inverse Compton scattering, where lower energy photons gain energy by interacting with high-speed electrons, can produce transient enhancements in optical wavelengths. Coherent emission processes, like those responsible for pulsar radio bursts, might also operate in the optical regime under extreme conditions. This could explain the extremely short durations and high brightness temperatures inferred for some ultrafast transients. Understanding which mechanisms dominate requires detailed modeling matched with comprehensive observational data across multiple wavelengths and time resolutions. Cross-correlation with signals detected in radio, X-ray, and gamma-ray bands enriches this multi-messenger approach. Furthermore, ultrafast optical transients may serve as probes of extreme physics beyond their intrinsic astrophysical interest. Their rapid timescales imply emission regions no larger than a few hundred kilometers, close to event horizons or neutron star surfaces, where strong gravity and quantum electrodynamics interplay. Such environments test our understanding of physics under conditions unattainable in terrestrial laboratories, potentially revealing new states of matter or quantum gravity effects. Observing deviations from expected transient behaviors could hint at phenomena such as vacuum birefringence, frame dragging, or even the influence of dark energy on light propagation. Moreover, UTs might also provide indirect evidence of phenomena such as Hawking radiation or exotic particles predicted by extensions of the Standard Model. Although highly speculative, such prospects energize the field, driving searches for anomalies and unexplained signatures in transient data. The detection of ultrafast optical transients also has implications for understanding cosmic magnetic fields. Magnetic field generation and amplification are fundamental to galaxy evolution, star formation, and jet formation. Observing transient optical signals linked to magnetic processes informs how these fields evolve and interact with matter under extreme conditions. From a cosmological viewpoint, studying UTs originating from distant galactic centers can shed light on the growth and activity of supermassive black holes across cosmic time. By building statistics on transient rates as a function of redshift, astronomers can trace how accretion and feedback processes have influenced galaxy formation and the intergalactic medium. In practical terms, the data volume generated by transient surveys is immense, necessitating advances in storage, retrieval, and analysis. Big data challenges drive the adoption of cloud computing, distributed databases, and high-bandwidth networking, facilitating rapid data sharing and collaborative research. Artificial intelligence, AI, and machine learning algorithms play increasingly vital roles in identifying, classifying, and prioritizing ultrafast transient candidates for follow-up. These systems learn from existing data to recognize patterns and reduce false positives, optimizing the use of limited observational resources. The public dimension of this research is also growing, with citizen science platforms enabling enthusiasts worldwide to participate in transient hunting. These initiatives democratize science and augment discovery potential by leveraging human pattern recognition alongside automated systems. Looking ahead, the field aims to construct a comprehensive census of ultrafast optical transients, linking them firmly to their progenitors and physical origins. Upcoming observatories like the Vera C. Rubin Observatory, with its rapid cadence survey capabilities, will provide vast datasets capturing transient phenomena across the sky. Similarly, proposed space missions focused on time-domain astrophysics with ultrafast optical capabilities promise breakthroughs in sensitivity and temporal resolution, enabling detection of fainter and more distant events. In addition to observational advances, laboratory astrophysics experiments replicating extreme magnetic fields and plasma conditions help constrain emission models. Facilities employing high-power lasers and pulsed magnetic fields simulate key processes thought to generate ultrafast optical transients, bridging theory and observation. The study of ultrafast optical transients from galactic centers sits at the nexus of astrophysics, fundamental physics, and advanced technology. These enigmatic bursts, fleeting yet powerful, open portals to understanding the universe's most violent and mysterious processes. Their investigation propels scientific innovation, challenges established theories, and enriches our cosmic narrative, revealing a universe that is not static but vibrant and transient in its very essence. As we continue to explore these brief but brilliant flashes, we edge closer to unraveling the secrets of the cosmos, one ultrafast burst at a time. Ultrafast optical transients from galactic centers also provide an unprecedented window into the interplay between dark matter and ordinary matter in the densest regions of galaxies. While dark matter itself does not emit or absorb light, its gravitational influence shapes the distribution and dynamics of baryonic matter, potentially affecting transient phenomena. The density spikes of dark matter around supermassive black holes, so-called dark matter spikes, could enhance interaction rates, creating conditions favorable for rare, energetic events that manifest as ultrafast optical flashes. Some speculative models propose that interactions involving dark matter particles, such as annihilation or decay near these dense regions, might generate bursts of electromagnetic radiation. Although no direct evidence currently links ultrafast optical transients to dark matter interactions, future observations could shed light on this tantalizing possibility, helping to unravel one of astrophysics' greatest mysteries. Another frontier is the connection between ultrafast optical transients and fast radio bursts, FRBs. FRBs are millisecond duration bursts of radio waves originating from extragalactic sources, some of which have been localized near galactic centers. The co-occurrence or correlation between FRBs and optical transients is a subject of intense research. Detecting simultaneous or time-correlated events across optical and radio wavelengths could confirm common progenitors or physical mechanisms. Such multi-wavelength coincidences would greatly enhance our understanding of the physics driving these bursts. For instance, magnetar flares are leading candidates for FRBs and may also emit brief optical bursts. Coordinated observational campaigns leveraging radio telescopes, optical observatories, and even X-ray and gamma-ray instruments are critical to capture these rare, simultaneous events. The rapid timescale of ultrafast optical transients pushes the limits of timing accuracy in astrophysics. To precisely characterize these events, absolute timing precision to microseconds or better is required. This demands sophisticated synchronization between observatories, often achieved using atomic clocks and global positioning systems, GPS. Such precision allows astronomers to cross-correlate events across different observatories worldwide, enhancing detection confidence and enabling detailed source localization. On the theoretical front, one of the biggest challenges is understanding how such intense energy can be released on timescales of milliseconds or less without violating energy conservation or known physical laws. Proposed mechanisms must account for how energy stored over longer periods can be suddenly liberated in a coherent, concentrated burst. Magnetic reconnection, crustal cracking in neutron stars, and relativistic shocks are among the few processes thought capable of such feats. The study of ultrafast optical transients also contributes to the broader field of time-domain astronomy, which focuses on how celestial objects change over time. This field is rapidly expanding due to advances in telescope technology, data processing, and global collaborations. Ultrafast transients represent the fastest-changing phenomena, offering unique insights into dynamic processes in the cosmos. Astronomers are now beginning to construct statistical models of ultrafast transient populations, assessing their rates, energies, and spatial distribution within and beyond our galaxy. These models help determine the frequency of such events and their contribution to the universe's overall energetic budget. Understanding these distributions is key to integrating ultrafast transients into broader astrophysical frameworks. As the field matures, standardizing data formats, observational protocols, and analysis techniques becomes essential. This standardization facilitates data sharing and comparison, accelerating scientific progress and reducing duplication of effort. International consortia and working groups are actively engaged in developing these standards. The potential for ultrafast optical transients to act as cosmic probes is immense. For example, measuring how their light is dispersed and delayed by intervening matter can reveal properties of the intergalactic medium, such as electron density and magnetic field strength. Such probes complement other methods like quasar absorption line studies, enriching our understanding of cosmic structure. Furthermore, ultrafast optical transients may serve as natural laboratories to study extreme plasma physics, including turbulence, particle acceleration, and wave-particle interactions under conditions impossible to reproduce on Earth. Insights gained here can inform other fields such as space weather, fusion research, and high-energy particle physics. The detection of ultrafast optical transients also raises intriguing questions about the limits of astrophysical observability. Could even shorter, more intense bursts exist, currently undetectable with present technology? The pursuit of ever faster detectors and higher sensitivity instruments is motivated partly by this possibility, opening new frontiers in astrophysical discovery. Engagement with emerging quantum technologies could revolutionize ultrafast transient studies. Quantum sensors, entangled photon detectors, and quantum timing standards offer pathways to unprecedented precision and sensitivity, potentially unlocking detection of fainter or more distant events. Collaborations between astronomers and physicists, engineers, computer scientists, and data analysts form the backbone of this multidisciplinary endeavor. The complexity of ultrafast optical transient research demands expertise spanning hardware design, theoretical physics, software development, and observational strategy. Looking beyond our own galaxy, studying ultrafast optical transients in distant galactic centers offers a glimpse into the universality of physical processes. Are these phenomena common across cosmic time and environment, or are they peculiar to certain types of galaxies or evolutionary stages? Large-scale surveys across various galaxy types and epochs aim to answer this. The search for ultrafast optical transients also intersects with the quest to understand cosmic explosions, such as gamma-ray bursts and supernovae. While typically longer in duration, these explosive events share some physical mechanisms with ultrafast transients, like rapid energy release and relativistic outflows. Cross-disciplinary studies help elucidate these connections. Importantly, the field continually evolves as new discoveries prompt re-evaluation of theories and methods. Unanticipated observations challenge existing models, driving scientific innovation. This dynamic process underscores the excitement and vitality of ultrafast optical transient research. In essence, ultrafast optical transients from galactic centers illuminate not only the most extreme corners of the cosmos, but also the frontiers of human knowledge and technology. They compel us to refine our instruments, sharpen our theories, and broaden our perspectives, pushing the boundaries of what we can observe and comprehend. As astronomers peer deeper and faster into the universe, these fleeting bursts serve as cosmic lighthouses, guiding us toward new realms of understanding and reminding us that even the briefest flashes can carry profound messages about the nature of reality itself. Ultrafast optical transients also present unique opportunities to test fundamental physics under conditions that are otherwise inaccessible. Near supermassive black holes, gravitational fields are so intense that they warp spacetime dramatically. Observing how light from ultrafast bursts is influenced by this warped spacetime allows tests of Einstein's theory of general relativity in its strongest regimes. Minute shifts in timing, frequency, or polarization of the burst photons can reveal effects like gravitational redshift, lensing, or frame dragging. Such tests are invaluable because they probe the fabric of spacetime itself and help constrain alternative gravity theories that seek to explain phenomena like dark energy or quantum gravity. Precision measurements of ultrafast transient signals may one day reveal subtle deviations from classical general relativity, potentially opening doors to new physics. Beyond gravitational effects, ultrafast optical transients may also help explore quantum electrodynamics, QED, in extreme environments. In the presence of ultra-strong magnetic fields near neutron stars or black hole magnetospheres, QED predicts phenomena like vacuum birefringence, where the vacuum behaves like a prism, splitting light into polarized components. Detecting polarized ultrafast flashes consistent with vacuum birefringence would provide direct experimental evidence of this exotic quantum effect. These bursts, therefore, act as natural high-energy particle accelerators in quantum laboratories, allowing us to observe particle interactions and radiation processes under conditions unreachable in man-made accelerators. Moreover, the extreme compactness and rapid variability of ultrafast transients suggest that they may be linked to the dynamics of relativistic jets, high-speed outflows of plasma launched from the vicinity of black holes. Understanding how these jets form, evolve, and produce radiation is a major challenge in astrophysics. Ultrafast optical bursts could represent brief shocks or magnetic reconnection events within these jets, providing clues about jet composition, speed, and magnetic field structure. Since jets influence galaxy evolution by regulating star formation through feedback, insights from transient studies have implications far beyond isolated bursts. Another exciting avenue is exploring whether ultrafast optical transients can be used as cosmic distance markers. Analogous to how Type Ia supernovae serve as standard candles, if certain classes of ultrafast bursts have consistent intrinsic luminosities or characteristic signatures, they could provide independent measures of cosmic expansion and help refine estimates of the universe's age and fate. Currently, the diversity of observed transient properties complicates this approach, but ongoing surveys and statistical studies aim to identify subclasses with stable properties. The role of machine learning in this domain continues to grow. AI models trained on existing transient catalogs can classify new events rapidly, identify novel patterns, and even predict where and when ultrafast bursts might occur. Such predictive capabilities could revolutionize transient astronomy, enabling targeted observations and maximizing discovery rates. In parallel, improved theoretical simulations using supercomputers are providing detailed models of transient progenitors and emission mechanisms. These simulations integrate complex physics including magnetohydrodynamics, radiation transport, particle acceleration, and relativistic effects, allowing researchers to generate synthetic light curves and spectra for comparison with observations. These computational advances are critical for interpreting the flood of data from modern observatories and for designing future instruments optimized for transient detection. International collaboration is paramount in ultrafast transient research due to the need for continuous, global sky coverage and rapid communication between observatories. Networks of telescopes coordinated across continents ensure that transients can be detected and followed up regardless of local daytime or weather conditions. Such networks also enable rapid multi-wavelength campaigns, essential for piecing together the full physical picture of transient events. Shared databases and open-access archives facilitate broader scientific participation and foster innovation. Beyond professional astronomy, the dramatic nature of ultrafast optical transients captivates the public imagination. These fleeting flashes, signaling cataclysmic or exotic cosmic events, resonate with fundamental human curiosity about the universe. Outreach efforts leverage this fascination to promote science education and inspire future generations of researchers. Educational programs, planetarium shows, and interactive websites featuring real transient data invite people to engage directly with cutting-edge science, democratizing discovery. From a historical perspective, the progression from the first tentative detections of transient astronomical phenomena to the current era of ultrafast optical transient science highlights the rapid pace of technological and conceptual development in astronomy. Instruments that could not previously capture millisecond-scale events are now commonplace, enabling new discoveries that redefine our understanding of the cosmos. Looking forward, the synergy between ground-based and space-based observatories promises to be transformative. Space telescopes free from atmospheric distortion can achieve unparalleled sensitivity and temporal resolution, complementing wide-field ground surveys. Planned missions dedicated to time-domain astronomy will expand our reach into the transient universe. In addition, emerging technologies such as adaptive optics, which correct for atmospheric blurring in real time, enhance the clarity of ground-based observations, further sharpening transient studies. As datasets grow larger and more complex, novel statistical methods and visualization techniques are essential to extract meaningful scientific insights. Data fusion methods that combine information across different wavelengths, timescales, and instruments enable comprehensive analyses. Ethical considerations regarding data sharing, resource allocation, and environmental impact of observatories are becoming increasingly important as the field expands. Sustainable practices and international agreements help ensure the long-term viability of transient astronomy. Ultimately, ultrafast optical transients epitomize the dynamic and ever-changing nature of the universe. They challenge us to develop new tools, rethink existing theories, and embrace the unknown. By probing these rapid flashes of light, we not only explore exotic astrophysical processes but also deepen our connection to the cosmos, revealing a universe alive with transient phenomena that flicker and fade, yet leave lasting impressions on our understanding of reality. This pursuit stands as a testament to human ingenuity, curiosity, and the relentless quest to uncover the mysteries written in the briefest glimmers of starlight. The investigation into ultrafast optical transients also intersects with the study of gravitational waves, a groundbreaking area that has revolutionized astrophysics over the past decade. Gravitational wave detectors such as LIGO and Virgo have opened a new window onto violent cosmic events like black hole mergers and neutron-star collisions, which produce ripples in spacetime itself. While gravitational waves carry information about mass motions and dynamics invisible to electromagnetic telescopes, ultrafast optical transients might represent the corresponding flashes of light associated with these cataclysmic occurrences. Detecting coincident signals. A gravitational wave event followed by or accompanied by a millisecond optical transient would confirm a direct link, enabling multi-messenger astronomy to probe the most energetic events in the universe in unprecedented detail. This synergy between gravitational wave and optical transient observations promises not only to validate models of extreme astrophysical processes but also to refine fundamental physics such as the speed of gravity and the behavior of matter under extreme compression. At the heart of many ultrafast optical transient studies lies the enigmatic environment of supermassive black holes, SMBHs, which lurk in the centers of most galaxies, including our own Milky Way. These behemoths, millions to billions of times the mass of the Sun, dominate the gravitational landscape of their surroundings and sculpt the behavior of gas, dust, and stars nearby. The accretion disks swirling around SMBHs are turbulent, magnetized, and prone to sudden energetic outbursts. Ultrafast optical transients could arise from abrupt magnetic reconnection events or shockwaves within these disks, analogous to solar flares but immensely more powerful. These sudden releases of energy on sub-second timescales challenge our understanding of plasma physics and relativistic environments, prompting development of new models and simulations to capture these explosive dynamics. In addition, the extreme gravity near SMBHs can compress and heat infalling matter to temperatures where it emits across the electromagnetic spectrum, including short, bright optical flashes that might be observed as ultrafast transients. Observing these bursts requires sophisticated instrumentation optimized for rapid response and high time resolution. State-of-the-art facilities employ fast photodetectors such as avalanche photodiodes and electron-multiplying CCDs capable of recording events down to microsecond scales. These detectors are often integrated into wide-field survey telescopes, scanning large swaths of the sky continuously to catch unpredictable bursts. Some experiments utilize high-speed imaging combined with real-time data processing algorithms to identify candidate transients immediately, enabling follow-up observations with larger telescopes or at different wavelengths. The challenges include minimizing noise, avoiding false positives from atmospheric scintillation or instrumental artifacts, and ensuring precise timing calibration. As technology advances, these detectors become increasingly sensitive and capable of capturing fainter, more distant events, pushing the frontiers of transient astronomy ever deeper into the cosmos. In addition to instrument development, data analysis techniques have had to evolve dramatically to handle the vast data volumes produced by modern surveys. Machine learning and artificial intelligence have become indispensable tools, automating classification of transient candidates and identifying subtle patterns beyond human recognition. These AI systems are trained on vast labeled datasets to distinguish genuine astrophysical signals from noise and artifacts with high accuracy and speed. Moreover, they enable anomaly detection, highlighting unusual or previously unknown types of ultrafast transients that might otherwise be overlooked. These discoveries can lead to entirely new classes of astrophysical phenomena, expanding our catalog of cosmic events. The interplay between human expertise and AI-driven analysis is a hallmark of contemporary astronomy, enhancing our ability to interpret the complex and fleeting signals emitted by the universe. One of the more intriguing theoretical prospects involves the role of magnetars, a special class of neutron stars with ultra-strong magnetic fields trillions of times stronger than Earth's. Magnetars are known to produce energetic bursts across the electromagnetic spectrum, including soft gamma repeaters and X-ray flares. Some models suggest that ultrafast optical transients could be generated during magnetar outbursts when magnetic field lines suddenly rearrange and release enormous amounts of energy. The rapid reconnection processes accelerate charged particles, producing coherent optical flashes lasting milliseconds or less. Detecting and characterizing such bursts would illuminate the physics of magnetars, their magnetic environments, and their contribution to the transient sky. Magnetars also present unique laboratories for extreme quantum physics, including tests of how matter behaves under ultra-high magnetic fields, making them central to studies of ultrafast transients. Beyond magnetars, other compact objects like pulsars and black hole neutron star binaries are implicated in ultrafast transient phenomena. Pulsars emit periodic radio and optical pulses due to their rapid rotation and strong magnetic fields, but occasional irregular bursts might be tied to star quakes or magnetospheric instabilities. Black hole neutron star binaries, on the other hand, may produce ultrafast bursts during close encounters or mergers, especially if tidal forces disrupt the neutron star's structure. These violent interactions could briefly heat and accelerate matter, leading to transient optical flashes that rival or exceed brightness of typical stellar explosions, but on far shorter timescales. Monitoring known compact object systems for such events is a growing focus of transient surveys, as it connects to fundamental questions about the life cycle of stars and the formation of exotic remnants. Understanding the progenitor populations responsible for ultrafast optical transients requires a multidisciplinary approach combining observations, theory, and simulations. Observationally, astronomers map the locations of detected bursts relative to host galaxies, star-forming regions, and other environmental factors. Patterns emerging from these spatial distributions provide clues about the age, composition, and evolutionary history of progenitor systems. For example, bursts clustered near galactic centers might implicate SMB-related processes, while those in star-forming regions might point to young magnet Rs or massive star remnants. Theoretical models then attempt to reproduce the observed burst properties, such as duration, luminosity, and spectrum, based on plausible astrophysical scenarios. High-resolution computer simulations, often requiring supercomputers, model the detailed physics of magnetized plasmas, relativistic jets, and shock waves to predict transient signatures. These integrated efforts are progressively refining the puzzle pieces that constitute the ultrafast transient phenomenon. The cosmological implications of ultrafast optical transients are also profound. Due to their extreme brightness and brief duration, they can potentially serve as probes of the early universe, allowing us to study conditions in distant galaxies billions of light-years away. If these bursts can be detected at high redshifts, they would provide unique insights into the formation and evolution of the first stars and black holes, the reionization epoch, and the buildup of large-scale cosmic structures. Their short duration means they can be used as precise timestamps for measuring the expansion rate of the universe and probing the intergalactic medium through absorption features imprinted on their spectra. This potential as cosmological tools makes ultrafast optical transients not only astrophysical curiosities but also powerful instruments for mapping the history of the cosmos. In the broader context of astrophysics, ultrafast optical transients complement other transient phenomena like supernovae, gamma-ray bursts, tidal disruption events, and kilonovae. While these longer-duration events have been studied extensively, ultrafast bursts occupy a unique niche at the shortest end of the transient timescale spectrum. This positions them as crucial missing pieces in the temporal puzzle of how the universe changes. Their study informs how energy is stored and released in extreme environments, how matter behaves under relativistic conditions, and how compact objects interact with their surroundings. Moreover, understanding ultrafast transients can shed light on the physics behind other transient phenomena, as some processes may share common physical origins or mechanisms. The development of global, coordinated transient networks is revolutionizing our ability to study these fleeting events. Facilities like the Zwicky Transient Facility (ZTF), the Vera-C, Rubin Observatory, formerly LSSD, and space missions like the Transiting Exoplanet Survey Satellite (TESS) are enhancing transient detection capabilities across multiple wavelengths. These observatories work in concert with radio arrays, X-ray satellites, and gravitational wave detectors to build a comprehensive, multi-messenger picture of the transient sky. Real-time alerts and data sharing enable rapid response observations, maximizing scientific returns from each detected ultrafast burst. This global cooperation exemplifies the collaborative nature of modern astronomy and underscores the importance of collective efforts in unraveling cosmic mysteries. Looking ahead, the next generation of telescopes and detectors promises to deepen our understanding of ultrafast optical transients significantly. Instruments with higher temporal resolution, greater sensitivity, and broader wavelength coverage will enable the discovery of fainter and more distant bursts, revealing the diversity of progenitors and mechanisms. Advances in quantum sensor technology, superconducting detectors, and photonic integrated circuits may revolutionize how we detect and analyze ultrafast signals, pushing observational limits beyond current capabilities. Additionally, space-based observatories free from atmospheric distortions will complement ground-based surveys, providing continuous coverage and access to wavelengths otherwise absorbed by Earth's atmosphere. The quest to comprehend ultrafast optical transients underscores the essence of scientific exploration, pursuing fleeting, enigmatic phenomena that challenge our understanding and inspire innovation. Each detected burst represents a fleeting message from some of the most extreme corners of the universe, carrying information about physics under conditions unattainable in laboratories on Earth. As we continue to develop the tools and theories necessary to decode these cosmic signals, we not only advance astrophysics, but also enrich humanity's broader quest to understand the universe and our place within it. These ultra-fast flashes of light remind us that even the briefest cosmic events can illuminate profound truths about nature, time, and existence itself. The fascinating realm of ultrafast optical transients also poses profound questions about the nature of cosmic magnetic fields, which play a pivotal role in shaping these explosive bursts. Magnetic fields permeate the universe on all scales, from planets and stars to galaxies and intergalactic space. But their origins, strengths, and topologies, especially in extreme environments, remain only partially understood. In the vicinity of compact objects like neutron stars and black holes, magnetic fields can become extraordinarily intense and tangled, facilitating violent reconnection events that unleash sudden bursts of electromagnetic radiation. Studying the polarization and temporal evolution of ultrafast optical transients offers a rare glimpse into these dynamic magnetic environments. Changes in polarization angle or degree during a burst can reveal the geometry and coherence of magnetic fields, helping scientists piece together how energy is stored and explosively released in magnetized plasma. Moreover, these investigations have implications far beyond isolated bursts, as cosmic magnetic fields influence star formation, cosmic ray acceleration, and galaxy evolution. The interplay between magnetic turbulence and relativistic jets from active galactic nuclei, often centered on supermassive black holes, is crucial in regulating feedback processes that determine the growth and morphology of galaxies. Ultrafast optical transients provide a unique observational window into these feedback mechanisms, allowing researchers to trace how tiny, rapid phenomena can ripple through cosmic structures on grand scales. Another intriguing aspect of ultrafast optical transients is their potential connection to mysterious fast radio bursts, FRBs, which are intense, millisecond duration radio pulses of extragalactic origin discovered only in the past 2 decades. While the physical mechanisms behind FRBs remain debated, some theories posit that similar energetic processes, such as magnetar outbursts or neutron star interactions, might produce both radio and optical ultrafast bursts. Detecting simultaneous or temporally correlated optical flashes alongside FRBs would revolutionize our understanding of these enigmatic signals, firmly linking multi-wavelength emission mechanisms. Coordinated observational campaigns combining radio telescopes and fast optical photometers are underway to test this hypothesis, marking the cutting edge of transient astronomy. The precise localization of ultrafast optical transient sources is another critical challenge and opportunity. Pinpointing the exact position of a transient in the sky enables astronomers to associate it with a host galaxy, stellar population, or known compact object, anchoring theoretical models to real astrophysical environments. Achieving arcsecond or better localization requires rapid, coordinated follow-up with high-resolution instruments. Technological advancements like interferometric arrays and adaptive optics are crucial in this effort. Improved localization also facilitates the study of the transient's environment, including surrounding gas density, metallicity, and star formation history, all of which influence the nature of progenitors and the physics of bursts. The discovery and study of ultrafast optical transients have also inspired innovative concepts in time-domain astronomy instrumentation. For example, projects aiming to build ultra-wide-field, high-cadence optical surveyors capable of capturing the entire visible sky every few seconds are underway. Such instruments would dramatically increase the detection rate of ultrafast events, uncovering rare classes of bursts and enabling statistical population studies. Combining these facilities with real-time data analysis pipelines will permit unprecedented reaction speeds to transient alerts, allowing multi-wavelength observations within seconds to minutes of detection. Scientific curiosity about ultrafast optical transients extends to their potential impact on nearby planetary systems and even Earth. While the majority of these bursts occur at vast cosmological distances and pose no direct threat, understanding the frequency, energy, and emission properties of such energetic events informs risk assessments related to high-energy astrophysical phenomena. For example, energetic bursts from magnet stars or supernovae in our galactic neighborhood could, in theory, impact Earth's atmosphere, potentially influencing biological evolution or technological systems. Studying ultrafast bursts adds to our knowledge of such astrophysical hazards, contributing to a broader field known as astrobiology and space weather. From a theoretical physics standpoint, the extreme conditions associated with ultrafast optical transients provide natural laboratories to explore fundamental questions about particle acceleration and radiation mechanisms. The rapid rise and decay times of bursts suggest extremely efficient acceleration processes, possibly involving relativistic shocks or magnetic reconnection zones where charged particles are boosted to near light speeds within milliseconds. The radiation emitted is often highly non-thermal, with spectral features hinting at synchrotron emission or inverse Compton scattering. Detailed modeling of these processes helps refine our understanding of plasma physics and relativistic regimes and informs the interpretation of observations from other astrophysical jets and shocks. Additionally, ultrafast optical transients are important for testing the limits of the so-called standard candle paradigm in cosmology. If subclasses of these bursts can be reliably characterized with predictable luminosities or spectral features, they might serve as complementary distance indicators to supernovae or gamma-ray bursts. Such standard candles are vital for measuring cosmic expansion and the parameters governing dark energy. Early investigations show promise, but the intrinsic diversity and complexity of ultrafast transient phenomena necessitate large, well-characterized samples before they can be confidently applied to precision cosmology. The international scientific community's embrace of open data and rapid alert systems has transformed the landscape for transient astronomy. Publicly accessible databases, coupled with standardized formats for transient event reporting, enable researchers worldwide to collaborate seamlessly. Citizen science projects have also harnessed the power of volunteers to sift through enormous datasets, identify candidate ultrafast transients, and flag unusual events. This democratization of data analysis accelerates discovery rates and fosters broader engagement with cutting-edge astrophysical research. Furthermore, the theoretical challenges posed by ultrafast optical transients have spurred cross-disciplinary collaborations. Plasma physicists, high-energy astrophysicists, computational scientists, and observational astronomers work in concert to unravel the complexities of these bursts. Insights from laboratory plasma experiments and magnetohydrodynamic simulations inform models of astrophysical transients, while observations feed back into refining experimental designs. This synergy exemplifies the holistic approach needed to tackle phenomena spanning immense scales of space and time. As research progresses, new classes of ultrafast optical transients continue to emerge, defying simple classification. Some events exhibit peculiar spectral signatures or repeat with irregular intervals, suggesting exotic progenitors or novel emission mechanisms. The diversity observed hints at a rich underlying astrophysical zoo, prompting the continuous revision of theoretical frameworks. These discoveries ensure that ultrafast transient astronomy remains a vibrant and evolving field, with many surprises still awaiting. On a philosophical level, ultrafast optical transients evoke profound reflections on the fleeting nature of cosmic phenomena and our human endeavor to capture them. These bursts flash and fade in milliseconds, ephemeral as cosmic fireflies, yet they carry messages from across billions of light-years and eons of cosmic history. They remind us that the universe is not static but a dynamic arena where energy is continuously transformed in dramatic and unpredictable ways. Our capacity to observe and understand these rapid events showcases the extraordinary reach of human curiosity and technology. The study of ultrafast optical transients from galactic centers represents a convergence of cutting-edge technology, theoretical innovation, and cosmic wonder. These fleeting bursts probe the extremes of physics, illuminate the workings of supermassive black holes and compact objects, and offer glimpses into the fundamental workings of the universe. Their investigation pushes the boundaries of astronomy and physics, challenging us to develop ever more sensitive instruments, sophisticated models, and collaborative networks. As we continue to unlock the secrets hidden in these millisecond flashes, we move closer to answering some of the deepest questions about the nature of matter, energy, space, and time. Each ultra-fast transient detected adds a precious piece to the grand cosmic puzzle, enriching our understanding of a universe alive with dynamic phenomena, forever changing yet eternally fascinating. The quest to understand ultra-fast optical transients also compels us to reevaluate the fundamental limits of observational astronomy, particularly how we perceive time and change in the cosmos. Traditional astronomical observations have often focused on steady or slowly varying sources, with changes measured over days, years, or millennia. However, the discovery of phenomena occurring in milliseconds challenges these conventions, urging the development of ultra-high time-resolution astronomy. This emerging discipline strives to capture the universe's most fleeting events, transforming our temporal window and revealing a hidden dynamism previously inaccessible. By pushing these limits, astronomers uncover transient phenomena that could hold clues about fundamental physical laws, from the quantum behavior of light to the dynamics of relativistic plasmas and extreme gravity. Within this context, the importance of temporal resolution cannot be overstated. Observations with millisecond or even microsecond precision require not only advanced detectors but also sophisticated timing systems synchronized to global atomic clocks. Such precision enables accurate measurement of burst durations, rise times, decay profiles, and even microstructure within the transient light curves. These detailed temporal signatures are critical for distinguishing between competing theoretical models, as different emission mechanisms produce characteristic timing patterns. For example, coherent emission processes might produce highly structured, periodic signals, while incoherent synchrotron emission typically results in smoother profiles. The ability to dissect these fleeting light signatures with exquisite time resolution is akin to opening a new sensory organ for astronomers, one that deciphers the universe's rapid heartbeat. Another fertile area of research concerns the energetics and emission mechanisms behind ultrafast optical transients. These bursts often exhibit luminosities that rival or surpass those of entire galaxies for their brief duration, implying extraordinarily efficient conversion of gravitational or magnetic energy into light. Unraveling how this energy is liberated so suddenly and efficiently remains a major theoretical challenge. Proposed mechanisms include magnetic reconnection events, shocks within relativistic jets, and sudden accretion episodes onto compact objects. Each scenario involves complex interactions between particles, fields, and radiation under extreme conditions. For instance, magnetic reconnection, a process where magnetic field lines break and reconnect, releasing stored magnetic energy, has been invoked to explain rapid energy releases observed in solar flares and is increasingly studied as a driver of ultrafast transients. Simulating these processes requires advanced magnetohydrodynamic models coupled with radiative transfer calculations, pushing computational astrophysics to new frontiers. Expanding our observational horizon, ultrafast optical transients might also arise from more exotic processes related to fundamental physics and cosmology. Hypothetical phenomena such as primordial black hole evaporation, axion star collisions, or interactions with dark matter could produce brief, energetic flashes detectable as optical transients. While speculative, these scenarios are grounded in emerging theories that extend beyond the standard astrophysical toolkit, linking transient astronomy with particle physics and cosmology. Detecting signatures consistent with these exotic processes would not only explain some ultrafast transient events but also open new avenues for exploring dark matter, quantum gravity, and the early universe's conditions. Thus, transient astronomy may become a powerful probe of physics beyond the standard model. A fascinating observational frontier involves searching for periodicity or repetition in ultrafast optical transients. While many bursts appear isolated, some show evidence of repeat bursts from the same source or exhibit quasi-periodic oscillations within their light curves. These features suggest stable progenitor systems or persistent mechanisms modulating emission. For example, rotating neutron stars with magnetospheres could produce periodic bursts as magnetic structures realign. Identifying and characterizing repeating ultrafast transients helps constrain source models and may reveal new classes of astrophysical objects. Long-term monitoring campaigns with high time resolution are essential to uncover these patterns, demanding coordinated global efforts and continuous sky coverage. The interplay between ultrafast optical transients and multi-messenger astronomy extends beyond gravitational waves and radio bursts. High-energy neutrinos, produced in energetic cosmic processes, might also be associated with some ultrafast transients. Facilities such as IceCube in Antarctica monitor the cosmos for these elusive particles, which travel unimpeded across vast distances, carrying information about hadronic processes inaccessible by photons alone. Coincident detection of neutrinos and ultrafast optical bursts would provide critical insights into particle acceleration mechanisms and the nature of cosmic ray sources. While such multi-messenger detections remain rare and challenging, ongoing upgrades to detectors and analysis methods continue to improve prospects. On the technological frontier, the challenge of managing the massive data streams generated by ultrafast transient surveys has driven innovation in real-time data processing and storage. Instruments operating at millisecond cadence produce terabytes of data nightly, necessitating automated pipelines capable of rapid calibration, event identification, and alert generation. Cloud computing, distributed processing frameworks, and machine learning algorithms have become indispensable for handling this deluge. These tools not only identify transients but also classify them, assess their scientific importance, and coordinate follow-up observations. This integration of big data science and astronomy exemplifies the modern era of data-driven discovery. In parallel, the development of space-based platforms dedicated to ultrafast transient detection offers unique advantages. Freed from atmospheric disturbances and day-night cycles, space observatories can provide uninterrupted monitoring across wide spectral ranges. Proposed missions with rapid imaging and photometry capabilities could detect ultrafast transients at wavelengths inaccessible from the ground, such as ultraviolet and soft X-rays, revealing complementary emission components and enhancing source characterization. Space-based detection also reduces background noise, increasing sensitivity to faint or distant bursts, thereby expanding the accessible volume of the universe for transient studies. Educationally and culturally, the captivating nature of ultrafast optical transients provides powerful opportunities for public engagement and science communication. The idea of capturing cosmic fireworks lasting mere milliseconds resonates with the human fascination for sudden, spectacular phenomena. Visualizations and animations depicting these bursts, coupled with accessible explanations, can inspire interest in astrophysics and technology. Citizen science initiatives that invite the public to participate in transient detection democratize scientific research and foster a sense of shared discovery. These outreach efforts strengthen the connection between science and society, emphasizing the value of fundamental research. In terms of future research directions, several key questions remain open. What is the full diversity of ultrafast optical transients, and how many distinct classes exist? How do these bursts relate to other known transients across the electromagnetic spectrum? What are the detailed physical conditions in progenitor systems at the moment of burst emission? Can ultrafast optical transients be standardized as cosmological probes? Addressing these questions will require advances across theory, observation, instrumentation, and data science, alongside international collaboration. Another exciting prospect lies in the intersection of ultrafast optical transient research with emerging quantum technologies. Quantum sensors and communication systems could enhance sensitivity to weak or highly coherent transient signals. Moreover, understanding the quantum properties of light emitted during these bursts might reveal novel physical effects or new quantum states of matter in extreme environments. While currently speculative, integrating quantum technologies into astrophysical instrumentation represents a promising horizon. On a broader scientific scale, the study of ultrafast optical transients exemplifies the shift from static to dynamic views of the universe. It highlights that the cosmos is a vibrant, ever-changing tapestry where phenomena occur on timescales from nanoseconds to billions of years. Capturing and understanding the shortest, most energetic bursts contributes to a holistic picture of cosmic evolution and energetic feedback processes. This dynamism influences galaxy formation, star life cycle, and even the conditions for life, linking small-scale bursts to grand universal narratives. The collaborative nature of ultrafast transient research also reflects the increasingly interdisciplinary and global character of modern science. Astrophysicists, data scientists, engineers, and theoreticians from around the world pool resources and expertise, transcending geographical and cultural boundaries. This collective endeavor not only accelerates discovery but fosters scientific diplomacy and shared human progress. Reflecting on ultrafast optical transients invites contemplation of our place in the universe. These ephemeral flashes, born in distant galactic centers or compact object environs, arrive at Earth carrying whispers of cosmic violence and transformation. Our ability to detect and interpret them speaks to the ingenuity and curiosity of humankind. In chasing these fleeting cosmic signals, we engage in a timeless pursuit, seeking to comprehend the universe's mysteries, however brief their illumination. Each ultrafast optical transient detected is a testament to both the universe's restless creativity and our enduring desire to understand the cosmos. The ongoing exploration of ultrafast optical transients from galactic centers also fuels advancements in computational astrophysics, where simulations must grapple with the sheer complexity of relativistic magnetized plasmas under extreme gravitational fields. High-fidelity numerical models now incorporate general relativistic magnetohydrodynamics, GRMHD, to replicate conditions near black hole event horizons. These simulations explore how accretion disk instabilities, jet launching mechanisms, and magnetic turbulence evolve on timescales comparable to those observed in ultrafast transients. The coupling of radiation transport codes with GRMHD models allows predictions of transient light curves and spectra that can be compared directly with observations, enabling a feedback loop that refines both theory and instrumentation. Emerging algorithms leveraging artificial intelligence and machine learning are revolutionizing the classification and discovery of ultrafast optical transients. With survey telescopes generating vast volumes of raw data, traditional manual vetting is infeasible. Instead, deep learning models trained on known transient classes can rapidly filter candidates, identify novel or rare phenomena, and predict the astrophysical origin based on photometric and temporal features. These AI-driven tools continuously improve through exposure to new data, adapting to evolving astrophysical knowledge. This dynamic approach is critical for keeping pace with the increasing sensitivity and cadence of observational campaigns. Intriguingly, some ultrafast optical transients challenge existing physical paradigms by exhibiting anomalous spectral lines or energy distributions that resist explanation by standard models. These anomalies hint at complex radiation processes, potentially involving exotic particles or unexpected plasma physics. For instance, some bursts show hints of cyclotron resonance features or rapid spectral evolution within milliseconds, suggesting highly magnetized, structured emission regions. Such observations push theorists to revisit assumptions about emission geometry, particle populations, and radiative transfer, inspiring new experimental and observational probes. Beyond the electromagnetic spectrum, ultrafast optical transients may play a role in the broader astrophysical ecosystem by triggering secondary phenomena. The intense burst can ionize surrounding gas, induce shock waves, or influence the local interstellar medium's chemistry. In some environments, repeated bursts might drive feedback loops that regulate star formation or modify the morphology of host galaxy nuclei. Understanding these feedback mechanisms requires integrating transient studies with broader galactic and extragalactic astrophysics, bridging microphysical processes and macroscopic cosmic evolution. The detection of ultrafast optical transients also motivates the development of novel detector technologies. Semiconductor-based photodetectors, superconducting nanowire single-photon detectors, and fast avalanche photodiodes are among the technologies pushing timing resolutions to nanoseconds and beyond while maintaining high quantum efficiency. Innovations in readout electronics, cryogenic cooling, and multiplexing increase detector sensitivity and reduce noise, crucial for capturing faint, rapid bursts from distant sources. Such technologies have applications beyond astronomy, including quantum computing, telecommunications, and medical imaging, exemplifying the cross-disciplinary benefits of transient research. Astrophysical surveys increasingly incorporate multi-wavelength and multi-messenger coordination, ensuring that ultrafast optical transient detections trigger observations across the electromagnetic spectrum and with neutrino and gravitational wave observatories. This holistic approach enhances the ability to build comprehensive source models by capturing complementary emission processes. For example, simultaneous X-ray, gamma-ray, optical, and radio observations can map the energetics and environmental impact of bursts, while gravitational wave detections confirm the involvement of compact object mergers. Such coordinated efforts require rapid communication networks, standardized alert protocols, and interoperable data archives. The population statistics of ultrafast optical transients are beginning to take shape, revealing clues about their cosmological distribution and rate evolution. Initial surveys suggest that these bursts are relatively rare but possibly undercounted due to observational limitations. Understanding their occurrence rates as a function of redshift informs models of cosmic star formation history, black hole growth, and compact object populations. Improved statistics will also refine estimates of their contribution to the cosmic energy budget and their potential role in shaping intergalactic environments. Ultrafast optical transients can also serve as probes of intervening matter along the line of sight. The transient light passes through interstellar and intergalactic media before reaching Earth, imprinting absorption features and dispersion signatures that encode information about the distribution, composition, and motion of intervening gas and dust. Detailed spectroscopic analysis of these features during bursts enables the study of cosmic structures otherwise inaccessible, such as the elusive warm-hot intergalactic medium thought to contain much of the universe's missing baryons. This technique complements quasar absorption line studies and enriches our understanding of cosmic matter distribution. Explorations into the polarization properties of ultrafast optical transients offer a wealth of diagnostic power. The degree and angle of polarization provide insights into magnetic field geometries, scattering environments, and emission mechanisms. Rapid changes in polarization during bursts may indicate evolving magnetic topologies or relativistic beaming effects. Polarimetric observations with high temporal resolution are technically challenging but invaluable, necessitating specialized instruments and data reduction methods. Advances in polarimetry promise to unlock new layers of information hidden within these fleeting cosmic signals. Theoretical models increasingly consider the role of plasma instabilities and turbulence in shaping ultrafast transient emission. Phenomena such as kink instabilities in magnetized jets or reconnection-driven turbulence can create filamentary structures and intermittent bursts of radiation. Understanding how turbulence cascades energy across scales helps explain observed variability and spectral features. Laboratory plasma experiments and space-based in situ measurements complement astrophysical observations, providing analogs to extreme cosmic conditions. In terms of cosmological implications, ultrafast optical transients hold potential for shedding light on the evolution of supermassive black holes and their host galaxies. Since many transients originate near galactic centers, their properties reflect the activity and environment of supermassive black holes, including accretion rates, jet dynamics, and magnetic field structures. Studying transient populations across different galaxy types and epochs informs models of galaxy evolution, feedback processes, and black hole growth mechanisms. These insights integrate transient astronomy with large-scale structure studies. The interplay between ultrafast optical transients and star formation is also a subject of active inquiry. Bursts associated with young stellar objects, massive star collapses, or magnetar bursts link transient phenomena to the life cycle of stars and stellar populations. These events influence surrounding molecular clouds through radiation pressure, shock waves, and chemical enrichment. Mapping these interactions helps clarify how transient bursts contribute to the regulation of star formation and the chemical evolution of galaxies. The potential for ultrafast optical transients to reveal new fundamental physics is profound. For example, if some bursts involve processes near or within the event horizons of black holes, they could provide empirical data relevant to theories of quantum gravity, space-time structure, and the information paradox. Observations of bursts that challenge classical predictions may hint at quantum effects or extra-dimensional physics, offering clues to unified general relativity and quantum mechanics. While highly speculative, this frontier represents one of the most exciting intersections of astrophysics and fundamental physics. In addition, ultrafast optical transient studies inspire the development of next-generation astronomical facilities. Proposed extremely large telescopes with segmented mirrors and advanced adaptive optics will push sensitivity and spatial resolution to new heights, enabling detailed follow-up of faint or distant bursts. Space-based observatories equipped with fast photometric and spectroscopic capabilities will complement ground-based efforts, creating a comprehensive network for transient detection and characterization. The synergy between these facilities promises a golden era for transient astronomy. Looking ahead, the integration of ultrafast optical transient data with other time-domain phenomena will deepen understanding of the universe's transient landscape. Connecting these bursts with longer-duration transients such as supernovae, tidal disruption events, or gamma-ray bursts helps place ultrafast events within broader evolutionary contexts. This holistic perspective enriches astrophysical narratives, linking the smallest, quickest flashes to large-scale cosmic cycles. Ultrafast optical transients from galactic centers represent a frontier where observational ingenuity, theoretical innovation, and cosmic curiosity converge. These millisecond bursts illuminate the most extreme physical conditions, challenge existing paradigms, and open pathways to new discoveries about black holes, neutron stars, magnetic fields, and fundamental physics. As technology advances and collaboration deepens, the secrets encoded in these ephemeral flashes will continue to unravel, revealing the dynamic and mysterious universe in ever greater detail. Our journey into understanding ultrafast optical transients is a testament to humanity's relentless pursuit of knowledge, fueled by the desire to capture the briefest, most brilliant moments in the cosmos. Ultrafast optical transients also serve as a critical testing ground for the physics of extreme environments that cannot be recreated on Earth. Near supermassive black holes at galactic centers, matter is compressed to densities and heated to temperatures that challenge even the most sophisticated laboratory experiments. Observing the rapid light bursts emitted from these regions provides empirical data on particle acceleration, radiation mechanisms, and plasma behavior under such extreme gravity and magnetic fields. These observations help bridge the gap between theoretical physics and observational astronomy, offering a window into processes that push the limits of our current understanding of matter and energy. The phenomenon of gravitational lensing introduces additional complexity and opportunity when studying ultrafast optical transients. Light from a distant transient source can be bent and magnified by massive objects like galaxies or galaxy clusters lying between the source and Earth, resulting in multiple images or light echoes that reach us at different times. In some cases, lensing can amplify otherwise undetectable ultrafast bursts, making them observable and providing a natural telescope to probe the distant universe. Analysis of lensed ultrafast transients can yield information about the mass distribution of lensing objects, including dark matter clumps, thereby linking transient astronomy with cosmological structure. Moreover, the extreme brevity of these bursts challenges the traditional paradigms of astrophysical event classification. Unlike long-duration phenomena such as supernovae or steady emissions from active galactic nuclei, ultrafast optical transients demand new taxonomies based on temporal, spectral, and spatial characteristics. Developing such classification frameworks involves statistical studies of burst properties, clustering analysis, and machine learning to discern patterns and subpopulations. These classification efforts are essential for understanding the physical diversity and evolutionary pathways of transient sources, informing both observational strategies and theoretical models. The role of magnetic fields in shaping ultrafast optical transient emission is a central theme in astrophysical research. Magnetic reconnection, the process believed to power solar flares, is a prime candidate mechanism for the rapid energy release in many ultrafast bursts. In the vicinity of compact objects, magnetic fields can reach strengths trillions of times greater than Earth's magnetic field, driving violent reconnection events that accelerate particles to near-light speeds. Understanding how magnetic topology evolves on millisecond timescales requires detailed magnetohydrodynamic modeling combined with observational constraints from polarization and spectral data, revealing the intricate dance between matter, radiation, and magnetism. Interestingly, the discovery of ultrafast optical transients has sparked renewed interest in the study of coherent radiation mechanisms in astrophysics. Coherent processes, where many particles emit radiation in phase, can produce extremely bright, short-duration bursts. Such mechanisms contrast with incoherent processes like synchrotron radiation, which tend to produce smoother and longer-lasting emissions. Identifying coherent emission signatures in ultrafast transients involves analyzing spectral fine structures, brightness temperatures, and polarization. Insights gained here could reshape our understanding of cosmic radio bursts, pulsar emissions, and magnetar flares, illustrating the interconnectedness of transient phenomena across wavelengths. The detection and analysis of ultrafast optical transients also have significant implications for the search for extraterrestrial intelligence, SETI. Some hypotheses propose that advanced civilizations might employ rapid, intense optical pulses for communication or signaling, as these bursts can stand out against astrophysical backgrounds. While no definitive evidence currently supports such artificial origins, the methodologies developed for transient detection can be adapted to search for technosignatures. This interdisciplinary overlap enhances the sensitivity and scope of both astrophysical and SETI research, emphasizing the broader scientific value of transient astronomy. On the observational front, the importance of wide-field, high-cadence surveys cannot be overstated. Instruments like the Zwicky Transient Facility, CTF, and the upcoming Vera-C. Rubin Observatory are revolutionizing the discovery space by scanning large portions of the sky multiple times per night, increasing the likelihood of catching rare ultrafast events. These surveys provide vast data sets that, when combined with rapid alert systems, enable near real-time follow-up observations across different observatories. The coordination among these facilities represents a paradigm shift in transient astronomy, fostering global networks that maximize scientific return. Another promising avenue involves the use of interferometry to study ultrafast optical transients with unprecedented spatial resolution. Optical interferometers combine light from multiple telescopes to achieve the resolving power of a much larger instrument, potentially resolving fine structures in transient emission regions. While challenging due to the short durations involved, advancements in fast timing detectors and real-time data processing may soon enable interferometric imaging of these fleeting events. Such capabilities would shed light on emission geometries, source sizes, and jet structures, providing direct spatial context to temporal and spectral data. The study of ultrafast optical transients intersects intriguingly with fundamental questions about the nature of time and causality in the universe. Millisecond and sub-millisecond phenomena probe temporal scales where relativistic and quantum effects may interplay, raising questions about the limits of classical causality and the behavior of information near event horizons. These transients could offer indirect observational windows into phenomena like time dilation, frame dragging, or even quantum entanglement on cosmic scales, stimulating new theoretical investigations into the fabric of spacetime. In considering the impact of ultrafast optical transients on galactic ecosystems, it is essential to explore their cumulative effect over cosmic time. Repeated bursts and energetic flares from central black holes or magnetars may inject substantial energy into the interstellar medium, influencing gas dynamics, star formation efficiency, and chemical enrichment. This feedback contributes to the regulation of galaxy growth and morphology, highlighting transient phenomena as key actors in cosmic evolution. Understanding these processes requires integrating transient observations with simulations of galaxy formation and evolution. From a methodological perspective, the calibration and characterization of instruments for ultrafast transient detection present unique challenges. Accurate photometry and timing require meticulous correction for instrumental effects, atmospheric variability, and background noise. Calibration strategies include the use of artificial light sources, standardized stars, and cross-calibration between different observatories. Ensuring data quality and reliability is critical for meaningful scientific interpretation, particularly when comparing observations across different instruments and wavelengths. The intriguing possibility that ultrafast optical transients may originate from previously unknown astrophysical objects or phenomena remains a tantalizing prospect. Just as the discovery of gamma-ray bursts revolutionized high-energy astrophysics, these fleeting optical bursts may herald the existence of new classes of compact objects, exotic states of matter, or novel astrophysical processes. Vigilance in data analysis, openness to unexpected results, and readiness to revise theoretical frameworks are essential components of this exploratory frontier. The integration of citizen science into ultrafast transient research amplifies discovery potential and public involvement. Platforms like Zooniverse enable enthusiasts worldwide to assist in data classification and anomaly detection, leveraging human pattern recognition capabilities alongside automated algorithms. This democratization fosters scientific literacy, inspires future generations of astronomers, and accelerates the identification of unusual transient events that might otherwise be overlooked. In an educational context, ultrafast optical transients provide compelling case studies for teaching astrophysics, data science, and the scientific method. Their extreme physical conditions, rapid variability, and observational challenges illustrate core principles in radiation physics, relativity, and computational analysis. Using real data and simulations in classrooms bridges theory and practice, engaging students with contemporary scientific challenges and techniques. The societal implications of ultrafast optical transient research extend beyond pure science. The technological innovations driven by the need for fast, sensitive detectors and data processing have spin-offs in communications, imaging, and information technology. Furthermore, the collaborative international frameworks built around transient astronomy foster global cooperation, shared infrastructure, and cross-cultural exchange, contributing to peaceful scientific diplomacy. As we deepen our exploration, interdisciplinary collaboration grows increasingly vital. Astronomers, physicists, computer scientists, engineers, and statisticians join forces to tackle the multifaceted challenges posed by ultrafast optical transients. This convergence enriches scientific perspectives, drives innovation, and ensures robust, comprehensive approaches to unraveling these cosmic mysteries. The philosophical reflections inspired by ultrafast optical transients invite us to reconsider our perception of the universe's tempo and scale. These ephemeral cosmic flashes, imperceptible to human senses without advanced instruments, remind us of the universe's complexity and our limited vantage point. They invite humility and wonder, motivating continual inquiry into the fleeting, dynamic phenomena that animate the cosmos. Our ability to detect and interpret these transients is a testament to human curiosity and ingenuity, a pursuit to capture the universe's briefest whispers and illuminate its deepest secrets. The very existence of ultrafast optical transients compels a reassessment of how time itself is measured and perceived on cosmic scales. These fleeting events, lasting mere milliseconds or less, demonstrate that the universe is not only vast in space but also profoundly dynamic in time. Our traditional views, often shaped by slow-changing celestial objects like stars or galaxies, must expand to accommodate phenomena that flicker and vanish in an instant. This challenges observational strategies and data analysis pipelines, demanding instruments capable of capturing, recording, and processing data at unprecedented temporal resolutions. It also forces astronomers to rethink how transient events fit into the broader cosmic timeline, bridging the gap between instantaneous bursts and long-term astrophysical processes. Delving deeper into the physics underlying ultrafast optical transients, the role of relativistic jets launched from black holes or neutron stars is paramount. These jets, composed of charged particles accelerated to speeds approaching that of light, can produce intense bursts of radiation when instabilities or shocks occur along their length. The interaction of these jets with surrounding material, magnetic fields, and radiation fields creates a complex environment ripe for transient phenomena. Detailed modeling of jet dynamics reveals how tiny fluctuations in accretion rates or magnetic field orientations can lead to sudden outbursts of energy, which manifest as ultrafast optical transients. Observing these events offers direct insight into the physics of jet launching and propagation, key processes in high-energy astrophysics. Moreover, the discovery of ultrafast optical transients has reinvigorated interest in magnetars, highly magnetized neutron stars whose magnetic fields can be 1,000 times stronger than typical neutron stars. Magnetars are prone to sudden magnetic reconnection events or crustal fractures that unleash massive amounts of energy in the form of X-rays, gamma rays, and sometimes optical bursts. Some ultrafast transients detected near galactic centers could be linked to such magnetar activity, possibly formed in the dense stellar environments there. Studying these connections helps unravel the life cycle of massive stars, the formation of neutron stars, and the influence of extreme magnetism on transient emission. The observational signatures of ultrafast optical transients also provide stringent constraints on fundamental constants and physical laws under extreme conditions. For example, measurements of the speed of light across cosmic distances and timescales test the constancy of this fundamental constant. Any variation could point to new physics beyond the standard model. Similarly, the interaction of transient photons with intergalactic media and potential quantum gravity effects could reveal minute alterations in propagation, such as dispersion or birefringence, offering rare tests of high-energy physics in situ. Complementing traditional electromagnetic observations, the emerging field of multi-messenger astrophysics enriches the study of ultrafast optical transients. Coordinated detections of neutrinos, gravitational waves, and cosmic rays alongside optical bursts deepen our understanding of the underlying astrophysical events. For example, a neutron-star merger detected via gravitational waves might produce ultrafast optical flashes as ejecta interact with magnetic fields. Similarly, neutrino detections associated with transients can pinpoint sites of hadronic acceleration, illuminating cosmic ray origins. These multi-messenger synergies amplify scientific returns, weaving a richer tapestry of cosmic events. The rapid rise of data-driven astronomy has profoundly impacted ultrafast transient research. The torrents of data produced by modern surveys require sophisticated storage, retrieval, and analysis infrastructure. Cloud computing, distributed databases, and high-performance computing clusters enable astronomers to process terabytes or petabytes of data in near real time. Advanced visualization tools allow researchers to explore complex multidimensional data sets, identifying subtle patterns and anomalies indicative of new transient phenomena. These computational advances are indispensable for converting raw observational data into physical insights. Another exciting development is the utilization of quantum technologies in ultrafast transient detection and analysis. Quantum sensors, entangled photon detectors, and quantum-enhanced timing systems promise improvements in sensitivity and precision beyond classical limits. These cutting-edge technologies could revolutionize how we capture faint, rapid signals from distant sources, potentially revealing transients that were previously inaccessible. The intersection of quantum technology and astrophysics exemplifies the continual innovation spurred by the quest to understand transient cosmic phenomena. The societal and cultural impacts of ultrafast optical transient research extend into the realm of public imagination and inspiration. Stories of sudden, brilliant cosmic flashes evoke wonder and curiosity, making compelling narratives for science communication, education, and outreach. They remind us of the universe's dynamic and sometimes unpredictable nature, fostering a deeper appreciation for the scientific endeavor. Engaging multimedia presentations, virtual reality experiences, and citizen science projects bring these phenomena into the public sphere, enhancing scientific literacy and excitement. In the philosophical domain, ultrafast optical transients provoke reflections on the nature of existence, observation, and the limits of human perception. These transient events occur at scales and times far removed from everyday experience, challenging intuitive notions of continuity and permanence. They illustrate that the universe is a mosaic of ephemeral moments as much as enduring structures. Such insights invite contemplation on the relationship between observer and observed, the flow of time, and the essence of reality as revealed through fleeting cosmic signals. From an engineering standpoint, the challenges of designing telescopes and detectors optimized for ultrafast transient detection drive advancements in materials science, electronics, and signal processing. Ultra-low noise amplifiers, fast analog-to-digital converters, and real-time data pipelines are essential components. Developing rugged, space-qualified instruments expands observation possibilities beyond Earth's atmosphere, where atmospheric distortion and absorption limit sensitivity. These engineering feats not only enable transient astronomy but also catalyze technological progress across multiple sectors. As the catalog of known ultrafast optical transients grows, comparative studies between different host galaxies reveal environmental dependencies. Factors such as galactic morphology, star formation rate, metallicity, and central black hole mass appear to influence transient characteristics and rates. Understanding these dependencies provides clues about the formation and evolution of transient progenitors and their interaction with host environments. Such studies contribute to a more complete picture of galaxy ecosystems and cosmic evolution. The theoretical landscape continues to evolve with proposals linking ultrafast optical transients to speculative astrophysical entities like primordial black holes, axion stars, or dark matter annihilation events. Although these ideas remain tentative, the unusual properties of some transients fuel exploration of these exotic possibilities. Confirming or refuting such hypotheses requires precise measurement of transient energetics, spectra, and localization, pushing observational and theoretical boundaries. This interplay between mainstream and speculative science enriches the field and broadens our horizons. The ethical dimensions of ultrafast transient research emerge in the context of resource allocation, environmental impact, and scientific inclusivity. Large observatories and data centers consume significant energy and materials, necessitating sustainable practices and conscientious planning. Ensuring equitable access to data and research opportunities promotes diversity and innovation, reflecting the global nature of astronomy. Embracing open science principles maximizes societal benefits and democratizes knowledge production. Interdisciplinary collaborations with fields like plasma physics, particle physics, computer science, and even philosophy expand the conceptual frameworks used to interpret ultrafast optical transients. Cross-pollination of ideas leads to innovative methodologies, fresh hypotheses, and novel experimental designs. These synergies exemplify how complex scientific challenges benefit from broad intellectual engagement beyond traditional disciplinary boundaries. Future missions specifically designed for ultrafast transient detection are under consideration, featuring specialized instrumentation such as ultrafast photometers, wide-field optical imagers with millisecond cadence, and onboard data processing units. These missions aim to systematically survey the sky for ultrafast events, building statistically robust samples and enabling rapid response follow-ups. They promise to fill observational gaps left by current facilities, accelerating discovery and characterization. Finally, the human element, the community of scientists, engineers, students, and enthusiasts, drives the field forward. Their curiosity, creativity, and dedication transform abstract data into meaningful scientific narratives. The collaborative spirit fostered through international consortia, conferences, and publications ensures continuous progress and adaptation to new challenges. Through their efforts, the ephemeral flickers of ultra-fast optical transients become enduring contributions to our understanding of the cosmos. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.